Hello everyone, this is Jason Kendall and welcome to the next of my introductory astronomy lectures. This time we're getting into the corpses of stars and what happens after everything has dead and gone in the stars. They've either exploded, gone into white, puffed off their outer layers as a planetary nebula. What is left from all those stars? We're going to begin with the low mass stuff, meaning white dwarfs. So we got two little videos coming up. The first is just on white dwarfs. The next one will be about novae and the type of supernova that happens with white dwarfs. So let's look at what a white dwarf is. Well, first we're going to look at this odd set of stars that are known in the HR diagram. We talked about this a long time ago in a previous lecture about what these are, but we never really discussed them very much. So there are some odd type stars way down in the lower left of the HR diagram, which tend to be very hot and extremely small. Their luminosities are very, very, very low, but their temperatures are high. Now, if their temperatures are high, because remember the temperature goes as the fourth power, and then if you multiply it, but if the luminosity's got to be low, then the radius has to be very small, that R sub star. So what we have is the T sub star, which is the surface temperature of the star, R sub star, which is the radius of the star, and L sub star, which is the luminosity of the star. So if we multiply the surface area of the star, 4 pi r squared, times sigma t to the fourth, which is how much energy is being emitted per square meter on the surface of the star, we get the luminosity. If it's a really, really, really small star, then it can be really hot, and that'll make it underluminous, and those are the white dwarfs. And we have two fiducial ones. One of them is Procyon B, and the other one's Sirius B. And Sirius B is a late O-type in its spectrum, and Procyon B is an early A-type star in its spectrum, but they're different in their spectra slightly. In any event, they're the weird ones in the HR diagram, and they're small. So let's go back and then look at how we know about white dwarfs, and we're going to go back to our original talk about binary stars. So if you have two binary stars, a binary star, true binary star pair, are pairs that are bound together by gravity. And more than half of all the stars in the sky have some stellar companion, at least two, and some have more. And the brightest star in the sky, which is only about 7 light years away, is Sirius, or Canis Majoris Alpha, or just the dog star. And the dog star is the brightest star in the sky. It follows Orion in the winter skies, so that's why it's the dog. So Orion's the hunter, and the dog follows the hunter, of course. So that's why it's Sirius, the dog star. And it's actually a binary star. And how we know that it's a binary star was back in 1844, the German astronomer Friedrich Bessel looked at the proper motion of Sirius. Remember, proper motion shows the motion of the star across the sky with respect to the background stars, and it must have had some sort of unseen companion. And we can look at this particular set of graphs, and the big dot on these graphs is the motion of the bright star Sirius A, the star that we see across from with respect to the background stars. And he deduced that there must be a companion because that big star was wobbling in the sky as it moved. So there had to be something affecting its motion. In 1862, Alvin Graham Clark also then observed the faint companion, which he called the pup, which is very cute, because it's Sirius B. So Sirius B means the second star in a multi-stellar system. So if it's a double star, we always start with the primary star, we'll call it A, and the second star we will call B. And distinguish it from planetary systems, we use capital B instead. But the binary companion, the dim companion to Sirius in the sky, is called the pup, and it is Sirius B. So in 1915, the spectrum was observed of Sirius B by Walter Sidney Adams at Mount Wilson outside of Los Angeles, and he found that it was a faint white star. And so he thought, wow, this is a white star. It means it's very, very hot. So the diameter was then determined back in 1959 to be very small, somewhere about the order of about the radius of the Earth. And in 2005, the Hubble Space Telescope team, a team using the Hubble Space Telescope, determined that it has that is nearly the diameter of the Earth, about 12,000 kilometers, and the mass of it is just a little bit bigger than the Sun. So something about the size of the Earth has the mass of just a little bit more than our entire Sun. Now remember, in terms of physical size, the Earth is about 100 Earths fit across the Sun. So it had to have been, whatever this thing that's that massive, had to be compressed down into something very, very, very small. So what do we mean by that motion, and how do we know this thing has that mass? And the first thing we remember is what we call a balance. We can think of it as a balance of forces between two things around a fulcrum point, and if they're in orbit around each other, they're going to orbit a common center of mass. So if something's got a low mass and it's far away, then it'll move fast. And in order to say the big mass, which is close to the center of mass, moves slowly, but they move at the same angular rate, meaning they seem to have a rigid stick between them, and that they don't really have a rigid stick between them, but we're using the teeter-totter as an example. So imagine now that this isn't just a teeter-totter, it goes all the way around. So these three people get a really fun ride, because now take the ground underneath from them, and they can spin round and round and round. And the people that are the two women on the right who are close in, they're not going to get too sick because they're close in, so they won't be moving as fast. But the guy way out at the edge, he's going to be moving very, very fast. And that's because the mass of the two that are close to the center is larger than the mass of the one way out to the edge. And so this balances them. So the mass of one must be balanced by the mass of the other, must be the distance. So the only way for them to balance like this is if that's the center of mass, or the center of balance, which is the fulcrum of the teeter-totter. So that's what we're explaining here, is that we have two mass stars, M1 and M2, and the little m star is low mass, and the big M star, M2, is higher mass. And so the fulcrum point is shown by the triangle where the center of mass is. And so if you put a stick between these two stars, it would balance right at that point, and we would determine that balance point in the following way. We'd say their average distance between them is A, and the sum of the distances between each of the center of mass, which is the triangle, to each of the centers of the stars is A1 and A2. And so if you add those two up, you get A, which is the average distance. And that average distance is what we used way back in Kepler's laws in order to determine the average distance between, say, the sun and the planet. But now that we're not saying a planet, we're saying two objects that are of similar mass, as opposed to, say, a satellite orbiting Earth or a planet orbiting the sun. We're saying two stars, so they're almost in balance. So the center of mass is outside of both stars. And in so doing, we find that the ratio of the masses, M1 to M2, where M1 is the little mass, compared to the distances between them, A2 and A1, are reciprocated. So you'll notice that if the M1 is smaller mass than M2, then it will be farther away than A2. So the smaller M1 is, the farther A1 must be for the lever arm to work. So we combine these two definitions of the speed that we saw in the previous slide with the distance ratio and the mass ratio to balance them, and then we plug them into Newton's version of Kepler's third law, which we have at the bottom, where we have p squared equals 4 pi squared, which is just some number, divided by g, which is Newton's gravitational constant, times the sum of the masses, and all of that ratio is multiplied by the average distance, a cubed. So if it's just a solar mass and p is measured in years and a is measured in AU, then you reduce all the way down to Kepler's law that he derived in 1610. However, we're looking at Newton's version, where the masses can be of equal or roughly of equal size, or at least any size, or a comparable size. And the periods don't have to be measured in years, maybe they're measured in days, and the average distance might be measured in like tenths of AU or something like that. But really we're going to measure the period in seconds, the masses in kilograms, and the A not in astronomical units, but rather in meters, so that G can have, the big G at the bottom, can have normal units associated with it. In any event, this is how we measure the masses of the objects, is by determining the period of the orbit and then determining the distance between them. So if we can determine their distances between them and determine how long it takes to do that, then we can determine the masses. And that can be done by looking at their actual orbits as they go across the sky. And as we saw before, there is a motion across the sky in proper motion. That when you take that motion across the sky and reduce it to the motion that they have orbiting each other, meaning let's just follow them across the sky. And instead of just saying, hey, look, they're going across the sky, look at their center of mass and see how they're orbiting their center of mass. And you get the two ellipses on the right. And where the graph meets in the center, that's the center of mass. So when they're far from the center, they're either far from the center of mass or they're as close they can be to the center of mass. And so they orbit as the dots, as you see in the arrows going around in the direction that you see. And every time there's a step of one dot, each of them goes a dot together. So when they're far from the center of mass, they go slowly, and when they're near to the center of mass, they go quickly, just as we expect from Kepler's law. So that means that Sirius B does a big loop, and Sirius A, the main bright star that you see in the sky, does a small loop. And that's what it means to have the braided motion that you see on the right, because the bright dot does a little motion across the sky, but the very difficult to see Sirius B star, which is very dim, does a big motion across the sky. And so we can actually reduce the proper motion to an actual distance motion by looking at how far apart they are. Now this data that we see here shows the actual position data sent relative to the bright star Sirius, which is now a dot, because now instead of saying, oh, let's look at the two ellipses, just center on the bright star Sirius and let's see how the other star, Sirius B, orbits it with time. And this is all the historical data that exists from 1862 to 2016, and this was compiled by Bond and his group in an Astrophysical Journal article on March of 31st in 2017. So this is pretty recent construction. And we see that there's photographic data, which is the blue data, lots of visual data as people have been doing things over 100 years. There's CCD imagery, as well as then the red imaging is Hubble Space Telescope imaging. And you can see that the Hubble Space Telescope provides some of the finest images along the line that really show exactly where it is in the sky. And this gives us an orbital set of parameters so we can actually see it. Now it's interesting that you don't see many data points when Sirius B is over on one side. And that's probably because, at some points in the year, well, Sirius is hard to view because the sun is in the same direction as Sirius. So it's very hard to get that data when it's over there on that side because the Sirius is up during the day. And so it's very hard to get that data. All right. So this is the orbital motion of Sirius B around Sirius A, which gives you the average motion, which gives you the period of the motion, how long it takes, and allows you to plug this into Newton's version of Kepler's third law in order to get the masses, or the sum of the masses. And if you know their relative distances, which we do because we can translate this angular distance that we see in the sky to an actual physical distance, because Sirius is so very close, it's only about 7 light years, that getting the physical size of this ellipse is actually pretty easy. So we use the physical size, we use the parallax of Sirius to get the physical distance. That allows us to know what the angular size that we see in this graph. Notice it says right ascension and declination, which gives you an angular size of that ellipse. And that angular size then can be translated into a physical size. Once you get a physical size, that is the A in Newton's version of Kepler's third law. And you can derive the period of the orbit from this kind of thing, and that gives you how long the period is. So you've got P for the period, A from the average distance between the two stars, and then that gives you, it allows you to derive the sum of the masses. And since we know their balance point, or their center of mass from the previous slide and the previous measurement, we then can derive the ratio of the masses. So now we have the ratio of the masses and the sum of the masses, which allows you to derive both of their masses. 2 equations, 2 unknowns, gives you a solution for both. That's how we know the mass of Sirius A and Sirius B. So that's called a dynamic value. And that allows us to get some interesting statements. And so here's the Hubble Space Telescope image from that time, and this was taken by Bond et al. For part of the study. And so that's obviously Bond's group has been part of has been studying this bright star because, white dwarfs are pretty cool. And this is Sirius B is this tiny dot, and there it is, and we see Sirius A in the background, which is overwhelming the light of Sirius B. But the statistics on Sirius B are interesting. It's a little bit bigger than the mass of the sun, meaning the mass is greater, but the radius is much, much, much smaller. It's less than 1% of the radius of the sun, or it's 0.8% or 84% of 0.84 of 1% of the radius of the sun, which means that's about 5,500 kilometers, which is about the size of the Earth. And the luminosity is very tiny, only 5.6% that of the sun. But the surface temperature is enormously hot, over 25,000 Kelvin, which is 4 times the temperature of the sun. So it's very, very hot. The average density, therefore, if we take the mass, and divide it by the radius cubed, 4/3 pi r cubed, we get an incredibly high density of 3 billion kilograms per cubic meter. That's a lot. 3 billion kilograms per cubic meter. We also can derive an age from Sirius B. It's only about 228 million years old, which means this whole star has lived its entire life in the time frame that it took the dinosaurs to become born as dinosaurs 250 million years ago, until they died out, and then we were born. So basically this star was born at basically the same time the dinosaurs were born on Earth, or at least arose on Earth. The progenitor mass of Sirius B was about 5 solar masses, so we know that in the process of losing mass, it lost 4 solar masses, or a good 80% of the mass of the star was lost in the evolution of the star. So about 4 solar masses of the material was lost to space as a planetary nebula, and the progenitor type star was probably a B-type star. So another way that Sirius B's mass could be measured, and this is what Joyce et al. Did in 2018, is, well, actually this is extremely recent, from September 4th of 2018. This is like right now. This is data that just came out in monthly notices of the Royal Astronomical Society, or MNRAS, and the monthly notice said that they discovered that the diameter was about 7,500 miles, or 12,000 kilometers. And what's fascinating is the gravitational field for something that massive would be about 350,000 times that of on Earth. So if you weigh 150 pounds right now on Earth, you would weigh 50 million pounds if you stood on the surface of Sirius B. And therefore, a teaspoon of this white dwarf material would weigh, just a teaspoon, wouldn't weigh a pinch, wouldn't weigh a gram. Like a teaspoon of salt is a couple of grams. No, a teaspoon of white dwarf would weigh 5 tons, which is about the same mass as 2.5 or 3 SUVs, which is crazy, or 2 Humvees. That's really very heavy. The light, therefore, from the surface has to climb out of a very strong gravitational field, and in so doing, loses energy and gets stretched to longer wavelengths. And this is predicted by Einstein's theory of general relativity, and it's called gravitational redshift. And that happens around massive, dense objects. So they warp space-time around them, and as so doing, they change the wavelength. And so what we can do is look for specific wavelengths of light, specifically hydrogen, because there is a thin, thin, thin atmosphere of hydrogen. I mean, really thin atmosphere of hydrogen, less than a few hundred meters thick at the surface of Sirius B. And we know that since it's extremely hot, it should emit in that characteristic frequency of H alpha. Now it's currently like an OB type star, so we do expect those kind of spectral lines. And so we look for the shift away from them. And so we have the equation down the bottom that shows what we're hunting for. And lambda sub infinity means what did we on Earth observe the wavelength of light to be. And it's important to view this from the Hubble Space Telescope, because you get a gravitational redshift very gently as the photon descends into the Earth's gravitational field. But you don't get that from Hubble Space Telescope as much, because you don't descend as far to the surface of the Earth. So lambda sub infinity is the wavelength that we observe, and lambda sub e on the bottom is the emitted wavelength of light. So we're going to get the ratio of the emitted wavelengths. We know what the emitted wavelengths of light, because we understand what hydrogen does. And so then you say, well, okay, we know what we see it to be, we know what it was emitted at, and then we can determine the radius of the object, because the radius and the mass. So the ratio of the mass and the radius is that gm 2gm over c squared r. And if we have some proper way of measuring the size of the object, then we can get the mass. And so basically they were able to derive a mass measurement and knowing the size of it. So the sizes can be the size can be determined basically from saying this is the Schwarzschild radius and how comparing it to the Schwarzschild radius, and that's what we get. So you can measure the mass of the object knowing its physical size by some hook or crook, meaning you have some radius measurement from, say, imaging, and then you determine by determining the spectrum of it, you can determine the wavelength that you observe it at, and you know the wavelength it was emitted at, and it allows you to determine the mass of the object. So this is how we know that the mass of Sirius B has 1.02 masses of the Sun by looking at the gravitational redshift of the light coming out of it. And I provided the two links there. That archive.org paper shows you exactly how they did this. And this paper came out on September 4th of 2018, which is really interesting. So there's ways you can derive the mass from the proper motion by looking at the motion of the two stars across the sky. And then there's a way of looking at the mass by measuring the size, by getting a size estimate, and then looking at the gravitational redshift. Then that'll give you the mass. And what's funny is they agree perfectly. So this is interesting to get two different ways of measuring things, and they agree. All right, so therefore we know the density is enormous because the mass is 2 × 10⁻30 kilograms. The radius is about 5.5 million meters, and that gives a density of about 3 billion kilograms per cubic meter, or approximately 3,000 tons per sugar cube, which is huge. That's a huge amount of mass. So that's a thing, that is a huge density for objects for such a tiny object. And this is how big they are with respect to the Earth. This is a nice artist's impression of how big a white dwarf is compared to the Earth. And if a white dwarf happened to pass this close to the Earth, or the Earth happened to pass this close to a white dwarf, well, that would be the end of the Earth. Because remember, a white dwarf has the mass of the Sun, so there would be enormous tidal forces across the Earth, and the Earth would be shredded by this. So this would be a way to die. And that's another funny name for this course is A Million Ways to Die. And a white dwarf passing right next to the Earth, a rogue white dwarf coming into the solar system, that would disrupt everything. Something the mass of the Sun passing through would basically tear the entire solar system apart, or at least send things flinging outwards and about. Even Jupiter would get flung out. Saturn would be flung out. The Earth would be torn to shreds if it got this close. Wow, what drama, and nothing could be done. Nobody could fly a spaceship and kick it out of the way. Oh, so sad. That's movie making 101. All right, so stellar graveyard. It's one of the many things that stars can end up with when they die. And a white dwarf is the core of a cold, dead star. And so as a star collapses, there's always this pressure, because remember, the whole thing, why stars do what they do is because gravity keeps pulling them in. And so some form of energy must be created or released in order to provide heat that provides pressure. And the pressure then resists gravity until there's something that either gets everything off of the thing in some great explosion like a supernova, or a planetary nebula pushes everything out in great thermal pulses so the weight's lifted, or the weight is never lifted and gravity keeps pushing and pushing and pushing until things get hotter and hotter and denser. Now, things collapse until there's new forms of pressure that take hold and allow a new form of hydrostatic equilibrium. But if it's too massive, then there's nothing that can hold it up, and it becomes a black hole, and we'll talk about black holes later. And all of these things are seen in the remnants of stellar evolution. So there's again the size of a white dwarf compared to the Earth, and interestingly enough, the escape speed, how fast you have to go from the surface of a white dwarf in order to escape. That's about 2% the speed of light. So in order to get off the surface of Sirius B, if you were standing there and then come home, let's say you took an Intrepid rocket and you landed on the surface of Sirius B, and somehow you survive the incredible heat and the incredible density and the incredible weight of your 50 million ton body, then that'd be tough. That'd be a really tough day, you know. But imagine you did that. But then you'd have to go 2% the speed of light just to lift off from the surface of that thing. That's really kind of fast. Not a lot of things have that kind of energy. So that, in fact, would be very difficult to make a rocket that could go 2% the speed of light. Nothing that's ever been built has, so that can't be done. And a white dwarf itself is a very, very strange object, and it has a degenerate matter core made of helium and carbon, and then a normal gas on top of it. Degenerate gas, normal gas, what do we mean? The normal gas is about 50 kilometers thick, or at the most, and basically once a white dwarf has been formed, they just cool off and become, after 10 or so trillion years, they finally emit all of their light and cool off to become a black dwarf. Now, the universe is only 13.7 billion years old, so no white dwarfs that have ever formed will have ever become black dwarfs. That will only happen in the deep, 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 deep future, long after the sun has died, long after the entire Milky Way galaxy has used up all of the gas and dust in it to make stars, long after all the other stars in the cosmos have gone out, and the only thing that's left are white dwarfs and neutron stars and black holes. That's what will be left, and these things will be spinning and emitting their heat for trillions of years and eventually cool to blackness. All right, so what do we mean by hydrostatic equilibrium? We're going to get into how white dwarfs hold themselves up against this enormous, enormous, enormous gravity and density. Well, remember that there's 2 points to this. At every layer in the star, and that's what that black dot thing means in there, is that at every radial point, every layer in the star, there's a balance between the gravity that's pushing it in from all sides and the gas pressure that's pushing it out from the center. And so something's got to provide the energy to give the pressure. Because remember, the star is leaking energy in the form of light. Because we actually see the star, we see the white dwarf, so it's cooling off. And the pressure there, and gravity doesn't cool off. Gravity always works to pull things together. So the gas pressure has to be provided by something, because that's the thing that's resisting the gravity. And as it cools off, the pressure reduces. So pressure and gravity oppose each other, and the gravity pulls it together, the pressure supports it, and when they're in balance, we call that hydrostatic equilibrium. Now, a white dwarf isn't actually collapsing. So how does it stay aloft at those incredible densities? But first, let's go back. Before we get to that, let's talk about what we mean by normal gases. So throughout the sun, even in the core of the sun, the ideal gas law, which relates the pressure and the temperature and how much stuff is in there and the volume, is how gases behave in the center of the sun. And that's pretty low density, low density. Remember we were talking about in the sun, the core of the sun could be as more dense than gold or lead by thousands of times. That's still considered low density for stars. That doesn't sound like low density for normal things to have something 1,000 times more dense than lead, but it is. So low density, and we're going to say, let's imagine that it's particles. Let's just say we only have electrons. Let's pretend we only have electrons. We, of course, have helium nuclei and hydrogen nuclei and all sorts of stuff in there. Mostly that, but it's like helium nuclei, hydrogen nuclei, and electrons are dominantly what's in the sun's core. And so when you compress them, they heat up. And so this gas law, which relates to pressure, volume, total number of particles, and the temperature T, and temperature T is related to the energy by that K number, which is Boltzmann's constant. And in the ideal gas law, these things don't actually stick together. They don't have any interaction except bouncing off each other. So the hydrogen nuclei, the helium nuclei, and the electrons just simply bounce against each other with energy in the same way that billiard balls on the surface of a table, or people playing any kind of ball game where the ball bounces against something or against other balls, how the balls stay like balls. They don't distort or go anything. Well, of course, if you look really close, a baseball does distort. But when we look at particles like electrons and protons, they don't distort. So they actually behave like really rigid billiard balls. And so that's why you get that nice little crack sound, because the balls actually just impact and the sonic, and there's some sound dissipation as they impact each other, which is a very complex process actually. But in any event, the particles simply bounce off each other and exchange energy in their bouncing. And that bouncing is what we call temperature, because they run into each other. Some are running fast, some are running slow, but on average, they have an average motion, and that average motion we call temperature, which then relates to the total number of particles, n, and the pressure, which is how big it is, and the volume in which they are operating, or the box in which they are. An alternate version of the ideal gas law, which is the same as previous, but a little different. So you have brackets around the P, which means an average pressure instead of pressure at a particular point and for a particular size of volume. We're going to average the pressure over a much, much larger area. That's what those brackets indicate. And now we have it in terms of the density. And rho, which kind of looks like a weird looking P, that is the average density, meaning number of particles inside or mass, the average mass of a particle divided by the volume inside of there. But we want numbers of particles. Remember, the previous equation had an n, so we have the average mass is what we divide that average density by. And then we still retain the kT. So notice that the ideal gas law basically says it's equal to pressure times the density times the temperature. Well, divided by the average mass. So the average mass is composed of, say, hydrogen nuclei or helium nuclei, or we just take the average mass of those objects. And that's what we really mean. So we've got the average mass of the thing, the average density, and then we've got the pressure. But here we have three things: pressure, density, and temperature are the main things that go into this. And that's what comprises normal gases. Normal gases such as the air you breathe, the air that's in a combustion engine of a car, the gas that's at the center of the sun, and the gas that's at the top of the Earth's atmosphere, and even the gas, well, to some extent, well, the gases that are in Jupiter's atmosphere and so on. So pretty much any normal gas that you will find, anything in a gaseous state on Earth, uses the ideal gas law to show how pressure, density, and temperature relate. However, in a white dwarf, all bets are off. We have a new type of gas law called the degenerate gas law. So at high density, this new gas law takes over because now we pack things in. We've said this is a very high density thing. So you pack everything into a really small volume. Everything is at these what we call low energy states, and only the high energy states are left, which is, what do you mean by that? And the result is what we call a degenerate gas. And the pressure then becomes independent of temperature, which is really weird. And so if you press on a degenerate gas, it doesn't get hotter. It just gets denser, which is weird. So if we press on an ideal gas, it can get hotter and not denser. It can say, I'm pressing on you. That means pressure gives it more temperature, and the temperature means average motion, which can keep the volume the same. But if you press on a degenerate gas, it gets smaller, because there's no temperature change, so the density goes up. Fascinating. All right, so to understand the degenerate gases, now we have to understand them really detailed, so we're going to get into some serious details here. And we're talking about what's called the quantum regime of gases. And this is when the electrons, specifically electrons and protons, get packed so tightly together that, remember we talked way back in the de Broglie wavelength, we said that the wavelength of an electron is what it has when it orbits the nucleus when an electron orbits a hydrogen atom. And the total number of waves in the wave in the orbit determines the distance that the electron is from the center. So an electron can be thought of, and in fact it is correct to think of it, as having a wave-like property. So if the distance between separate electrons is on the order or very close to the size of their wavelengths, then we have to worry about quantum effects. And that's what happens at the densities of a white dwarf star. So a couple of things come into play, and the first is called the Heisenberg uncertainty principle, which says that you can't, if you really know the position of something, you can't know where it's going to be next. Or equivalently, if you know how much energy an electron has, then if you really, really are accurate about how well you know the energy, you will never know when exactly it had that energy. which is kind of a weird way of saying it. Or if you know exactly when it had the energy, you don't know what that energy is now. And that's what this equation at the bottom expresses. It says the product of delta x, which is where it is, times delta p, which is its momentum, or how fast is it moving times its mass, or where it's going to be next. The product of those two things must be bigger than some really tiny number. So this is actually that h bar over 2 is so small that it doesn't really matter in the large world. And it applies even in normal stuff, but that in normal size scales, but h bar is so small that we don't notice it. But in the quantum regime, when you're looking at things that are very high density and looking at very short time scales, then this really starts to matter. So delta x shows, let's say it's the characteristic size of an electron, or remember the de Broglie wavelength is said that the momentum is related to the wavelength. So in fact, they're the reciprocal. So what we have then is that the size of the object, delta, or you can even say where it's confined, the physical location it's confined. If you can really nail it down with, say, a pin, like a butterfly in a box, then you'll never know where to be next. Literally, you can pin it for the shortest period of time, but when you lift that pin up, or even you will have no idea where it's going to be after you measure where it is. That's what we mean by this. It's a very strange principle, the Heisenberg uncertainty principle. And second, we have what's called the Pauli exclusion principle. And this is the other thing that happens. No two electrons or no two particles can have the same energy, position, or state. And that's a very strange thought. What it means is that there's also another quantum mechanical concept called spin. And that's what we have with the 21 centimeter radiation that we're going to talk about extensively well, we already talked about that in looking for the cold gas in the Milky Way and looking at places where star formation exists. But when you have an electron can either spin up or spin down. And it can be either here or there with this momentum or that momentum. But no two identical electrons. And all of the electrons are exactly identical. So the only thing that separates an electron from another electron is where it is, what its momentum is, and what its spin is. And no two electrons can have the same quantum numbers of location, momentum, and spin. And when you get them really packed together, this becomes important. It doesn't really matter too much when they're far apart, but once you get down to white dwarf size, it's like, oh, you got that one, I got this one. So I'm keeping this, I'm going to keep, if you're here, but I got to have a different momentum just to be right on top of you. So you can have electrons on top of electrons so long as they have different momenta and different spins. Let's see what that works like. We're going to now consider what we call a one-dimensional example, where we're only going to use the left and right, which is delta x, confine it into a box going left and right. And we're going to look at the energy in form of momentum, which is p, going up and down. So the little squares are left and right position, meaning the delta x. And the delta p shows up and down for the energy. So really, we're kind of playing a little fast and loose with this, but just bear with me a bit. We can relate very easily the momentum to the energy. But you know, for those that are following along at home that really know what we're talking about, are going, wow, you're already violating some stuff. But basically, we're saying position and energy. Effectively, that's what we're saying. So what the little box says is that the electrons can either have a green arrow up, and that's spin up, or a green arrow down, spin down. They can be somewhere left and right, that's their position, or they can have energy, lowest energy at the bottom, highest energy at the top. All right, so so there are many, many, many boxes, and almost all of them fill the lowest energy states. Why? Because that's the lowest energy state, and most things have low energy, unless, of course, something comes along and gives them a kick. So when you pack things together, even in the gas like you breathe, if it had high energy, we would call that a high temperature, and it would be hot. And so things would be in upper energy boxes. So when it's colder, everything goes to lower energy boxes. They don't change their positions, or they do because they're bouncing into each other all the time, but they don't go up because they don't get much energy because it's cold. So when we compress the boxes, let's say we compress it from left to right, or the right-hand side, we're going to compress to the left. So there's 16 boxes going across. Let's say we compress it to the left, and we compress it down to 7 boxes. So some of these boxes will be filled at the bottom if we compress it very slowly and don't add heat. And that's called an adiabatic compression. And so we would allow it to be we'd compress this thing, and so that we could get more heat, things would stay in the low energy state, and then only the ones in higher energy states would be left. So as long as it can transfer heat around, then things will be in these low energy states, or high. They can be in both. But the point is there's lots of empty spaces for things to go to. Let's see how that works. So let's see how energy exchanges in a normal gas. So this is an example of a normal gas, meaning lots of open space. Spins are roughly randomly oriented. Most things are in the low state. And as you go upper and upper in the upper level states, there's fewer and fewer, but there's lots of space. And not everything's packed. You can see that you could pack them, but they're not. So let's look at one, and let's say two electrons approach each other. Remember, left and right means that's their separation physically. So as they approach each other, they get closer, and all of a sudden they're on top of each other. Remember, electrons have wavelength, so it's like this superimposition of two waves. And when they collide, it's like the two waves collide. And as they collide, they exchange energy, and one of them loses a little bit of energy to the other, and the other one gains a little bit of the other's energy, and then they move apart after the collision, and that means that they've exchanged energy. So the two electrons have exchanged energy, interacted, bounced off of each other, and they can do this freely and go across each other. But notice for a short period of time, they occupied exactly the same space, but because they have a wavelength, because electrons have a wavelength, they had different energy, they could meet and keep going, but the momentum meant that they had to keep moving. And so when we average over the huge number of atoms that we typically, or electrons, that we typically have in a hot ionized gas, that this is what we call temperature, and that's what we call heat, is the average motion of all these electrons throughout as they interact and bump into each other. All right, so now let's see what happens when one bounces off what we might call a wall. So the wall might be the bottom, or the left-hand side we're going to call it a wall. And so we have an electron goes to a barrier, it goes and hits the wall. Now let's pretend that's actually the bottom. So maybe the electron hits the bottom of the box, or whatever it is, and there's nothing below it. In fact, that is the very core of the star. So it bounces off the core, loses energy because it's imparting that energy either to a wall, maybe it's just a normal wall because the gas in a room bounces off a wall and imparts energy, so that's why the air temperature, if it's hot in the room, the walls become warm too, because as the gas bounces against the wall, it imparts energy to the wall, and the gas that moves away from the wall. So you can see that the electron bounces on the wall, gives it the energy, and moves away from the wall. Left and right is movement left and right. Up and down is movement of energy. So eventually, these things collide and collide and collide and bounce off of each other, and if they interact with the walls and the walls don't steal the energy, then there's a total sum of energy and things eventually bounce into each other, and this would be like a little mishmash. And it might look, I mean, I can't do the animation because that would take me really long, but just think more that it's like the balls that you come up in like a Powerball sort of, or a lottery thing where the balls are popping up and popping up. That's much more like what we're talking about here. And these things would be moving and jumping and bouncing into each other, and some of the high energy ones would hit some of the lower energy ones and impart energy to them. But the total sum of all the heights and the total sum of all the heights that exist in here would be the total amount of energy in the system. So notice that you could sum up, okay, the ones on the far right, one of them has 2 energy points and the other one has 5 energy points. And you could say how high they are up from the bottom, where the bottom is 1 energy point. But since it's a ground state, we might want to say it's a 0 energy. So we could call the bottom one 0, and the second row, or the second story on this graph, the 1 energy point. So that would give us the total amount of energy. And if it doesn't leave by leaking left and right into the walls, then these things would be bouncing into each other, and occasionally the ones in the bottom would go up high. And sometimes some of them would have all the energy go way up high, but they would lose that energy rapidly and drop back down. So on average, that total number of heights of all of the all of the arrows from the bottom would be averaged over all of them, and not one of them wouldn't have all of it, but because that would mean that they keep bouncing into each other and losing the energy to that one, but that thing's going to be bouncing into others and imparting that energy. So when two came, they exchanged the energy. So you can exchange energy, and the total sum is constant inside the box. That's what we were talking about. So now let's compress it. Let's see what happens if we push it. So we're going to take a piston. So that red bar on the right-hand side is now a piston, and we're going to push on this box and make it smaller. And let's see what happens. First, the electrons try to push back on the piston by giving it energy to say, now you stay away, and they give the energy, and the piston says, okay, I'll stay away. But that imparts energy to the piston, warming the piston, but cooling the gas. And if the piston is relentless, it will push on the gas until it pushes them. But if the piston then pushes on it, it reduces the size, which then raises the temperature, just like a normal gas, like a PV-nRT. We've made the volume smaller, which has raised the pressure, which has given temperature, which has imparted more, given it some kind of, push the ones in the lower boxes up, so that it actually forces energy into the system. It gives it more height in this diagram, if you will. And so the more we compress it, we give the electrons energy and they hop up. So we keep pushing on the piston, and it heats the gas by moving the electrons, which are these arrows, up into upper states. So now the electrons go up, and therefore they have more energy, so they're bouncing around. Of course, the graphic doesn't show that. It's very too difficult for me to do all that, so I did not do it. So that gives them energy, and they're going to be bouncing all over the place. And as we can see, they can bounce off of each other and reduce that energy. They can also bounce into the wall and reduce down and impart the energy and try to keep the piston up. But notice what we also have here is that the electrons can pack into a box, so long as one of the boxes has spin down and one of the boxes has spin up. So long as you can't have two spin ups in one box, you can't have two spin downs in one box. And that means they can occupy the same exact space and have exactly the same energy, so long as they have different spins. And that's what we're going to start to do now. Let's really push on this thing. We're going to press with this piston relentlessly, never stop pushing, and compress this thing down to a really small space. Boom. Now, if you keep pushing and pushing and pushing and pushing, then all of a sudden, eventually, over time, and if the pushing eats the energy, then what's going to happen is all the electrons will be packed down into the smallest possible volume. They'll all have everything will lose all its energy. It'll be pushing against the piston, but notice it can't compress anymore. There's no place for it to go. It can't be pushed into. And basically, in order to actually push into it, the piston has to now impart energy. It has to give energy into the system instead of letting the energy redistribute, because that's what we did before. We let the energy redistribute. But now, in order to push this thing smaller, make it less than 6 boxes left and right, the piston has to say, I'm a hot piston, I'm going to push on you and go impart more energy. So let's get rid of the piston for a bit and pull all the way out and look at the side. The way we can now think about it is that we can say the whole box is being pushed at from the right by the self-gravitation of all of the electrons themselves. So now there's no piston. Let's pretend there's no piston. And what we have is that the electrons are packed together. The gravity from all of these things is so strong because they're really pulling on each other. So the self-gravitation is the piston. So the left-hand side of this box might be the center of the star. The right-hand side of this box might be the surface of the star. And so now we see that they've imparted all their energy to try to get rid of it. It's gotten rid of all this energy, but now the electrons are in these low states. They can't do anything. So to actually compress them, you have to give energy into the system in order to move the electrons out of the box and up in energy. So notice they're occupied the bottom 3 rows, and there would be more energy in order to go to the 4th row. And if it's gravity, just is like saying, I'm not going to do anything because I'm compressing you. So this is a stable state because now this is the self-gravitation of all of these electrons on each other, and they're in their lowest possible state. And this is what we mean by a degenerate gas. A degenerate gas is compressed maximally. All of the electrons in an electron degenerate gas, they all occupy the lowest possible energy states. They all occupy both the lowest energy states, and they're compressed together such there's no physical space between them. And this acts like a brick wall that supports the self-gravity of each other because they can't go anywhere. You can't put 4 electrons in one box. You can't put 3 electrons in one box. You can only put 2, and 1 spin up and 1 spin down. That's the Pauli exclusion principle. And now the Heisenberg uncertainty principle says that you don't know what's going to be happening next to any one of these. Because notice that these things are here in these boxes, but because they're individual electrons, they can be jumping from point to point to point, and you can't tell. Because the one of them will become the other, and the other will become the one, and they'll actually be moving around inside of there, but they're all identical, so it's as though they're staying still. So if you push on it harder, then you have to impart energy. So if the only way to do that is if the self-gravitation somehow overcomes it, maybe there's too much mass, and the gravity gives a little bit more energy, it forces them out into the upper level. Now you've got this gas that's bouncing off of it. But the funny thing is that those top layer, notice if it bounced against the wall of the bottom or the wall of the top, they can't cool down. So now in the previous examples, we had the electron gas cooling down by bouncing against the wall and moving to a lower energy level, meaning down the stack. None of the ones that we just bumped up can't actually cool, so they stay hot. That's very strange. So we can think of them as in their lowest state. They're very, 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 very hot, and they can't cool down. There's no way for them to cool down because cooling down means going to a lower energy state. They can't do it. So as you compress a degenerate gas, you're forcing them to have more and more and more energy, which means there's no way for them to lose this energy, so they stay energized. And the energy is provided by the pressure due to the self-gravitation of all the electrons pulling on each other. So all these green arrows have mass. And because they have all mass, they're all pulling on each other. And as they're pulling on each other, that's the self-gravitation of all these green arrows pulling on each other. All right, so that's what we mean by the self-gravitation. They pull together on each other. And this piston is unstoppable because it's gravity. It never ends. That they can never cool down. The only thing that could possibly happen is, what if we add more mass? Well, that adds more self-gravity. Maybe we add more layers on. That means that if you add more electrons to this box by dumping them on from, say, the right-hand side, let's say the left-hand side, the center of the star, the right-hand side is the surface. If you dump electrons on from the right, they have to land on it with high energy. If they land on it with high energy, they stay hot. There's no way for them to cool down. They become part of the degenerate electron gas. In a very real sense, we can think of this as like a big subway car. So start way uptown in New York City. You start on the end of the A line with nobody in it, and a couple people sit on the lowest, get seats. And so you get to a few stops down, every seat's full, and so everybody's seated. And now the next stop, after everybody's seated, people get on and they're standing room. And so that's the second level, the standing room. Eventually you get long enough that there's the standing room's filled. And let's say it's an extraordinarily busy day and people still keep packing in. Well, where are you going to go if all the seats are taken and everybody's already standing? Well, you get on top of people's shoulders. That's the third level. And so now we're up on top of people's shoulders. And people are getting really irritated with that because people are on top of your shoulders. So they're going to shove you around. So the people that are on top of people's shoulders get shoved around until they never stop moving. That's the third level. Well, we keep going down the subway line. Now we get to Times Square. Now we've got people seated who aren't getting off. People standing who say, I'm not going to give up my standing spot until I get a seat. And the people who are being shoved around above on top of those people, like at some crazy concert, they try to get on. That's the fourth level. And they have to get on top of the people who are being shoved around. So everybody's annoyed. So a degenerate gas is a whole bunch of people in the subway car that can't leave the subway car. The subway car is not getting any bigger, and everybody's just getting more energy as you keep packing stuff in. Here, energy equals anger or heat, because they broke the air conditioning too, just to make it fun. So you can't cool off, you can't get off, and you can't leave, and you can't sit down, and you can't stand. That's the electrons in a degenerate gas in a white dwarf. All right, so what does that mean? White dwarfs cannot cool, so therefore the pressure is not dependent on the temperature, it's only dependent on the density. So remember we had from before the ideal gas showed pressure equals some density times some temperature. Well, now we are different. We have pressure equals some constant number times the density to the 5/3 power. That's kind of weird, but look at the constant. I just said pressure equals some constant. Look at the constant below. Don't worry about that. That's just what you'll find if you go hunt around on Wikipedia. It's based off of the mass of the electron, the mass of the proton, and Z over A is equal to the total number of particles compared to the atomic number to 5/3 power. And there's a pi and an H, which tells you it's a quantum effect. But basically, the pressure is to the density to 5/3 power. The funny thing is that if you looked at the temperature, if you took the energy that's imbued inside a degenerate gas and spread it out, it would be though that the electrons have a temperature of billions of degrees because they're occupying so much of the energy. Remember, the energy is how high the sum of all the boxes are off the ground with all the electrons. So really, there's a huge amount of energy inside of it. It just can't cool off. So it would be the equivalent of it being billions of degrees if they were free to move. But they can't move. They're being compressed by their self-gravity. So what does this mean for this? Let's kind of get an idea of where the density comes from. This is the central pressure of the core of the sun, and this comes from a previous lecture. So let's kind of go blazingly through this. The pressure at the core, P sub C star, sun, which is the circle with a dot in the middle, that's the pressure at the core of the sun, is basically the mass of the sun divided by the total mass of the sun divided by the total radius of the sun squared. That's roughly it, times the gravitational energy of the entire sun, which is G, m mass of the sun divided by the radius squared. So the pressure at the core of the sun roughly goes like the Newton's gravitational constant G times the mass of the sun squared divided by the radius of the sun to the 4th power. It's roughly where that comes from, and that comes from the stellar structure equations we see on the upper right. And giving that kind of thing, it tells us that the central pressure of the sun is something like 10 to the 16th pascals, or 100 million times what it is at the bottom of the Mariana Trench. And normal air pressure is about 10 to the 5th pascal, so that's pretty dense. What's funny is, even at that high pressure, when it's tens of millions of degrees, that's still a normal gas because the temperature is enough to keep it not degenerate. All right, but white dwarfs are smaller. Well, let's take that equation that we had for pressure, where pressure equals gm squared over r to the 4th, but instead of using the pressure due to an ideal gas, now we're going to use the pressure due to a degenerate gas. And that tells us an interesting thing. Pressure degenerate is rho to the 5/3 power, which is like the mass divided by the volume cubed, which is radius cubed. And that's what we mean. That's where that m to the 5/3 and r to the 5th power comes from on the right-hand side. So now we can equate those two things, which is the self-gravitational pressure, gm squared over r to the 4th, which is the pressure due to the entire star pressing on itself, due to gravity, and we equate that roughly to the degeneracy gas pressure, which is m, the mass of the star to the 5/3 power divided by the radius to the 5th power, and solve the algebra, and we find that the radius of a white dwarf is proportional to the mass to the minus 1/3 power. That's very, very strange. The more massive a white dwarf is, the smaller the radius. That's what the thing in green circle says. So if you had a white dwarf with 10 solar masses, which doesn't exist, but let's pretend it is, and there's something, maybe a different white dwarf that's 1,000 times more massive than the previous white dwarf, then if you have something 1,000 times more massive, then it will be 10 times smaller. So one object, something 1,000 times more massive will be 10 times smaller in radius. That's crazy, but that's what happens with the degenerate gas, and that's what happens with white dwarfs. So the more massive they are, the smaller they are. So that doesn't last forever, because the mass, if it goes up and up and up, that would mean that the larger the mass, the radius gets tinier and tinier until you could imagine that the mass could become infinite. Imagine there's stuff that just never stops dumping on top of the white dwarf. It would get smaller and smaller and smaller until it became the size of a speck, or zero size, which is bizarre. So that can't happen. Why can't that happen? Because as the pressure goes up, it gives the electrons more energy. The energy then becomes like a speed, and speed means they're bouncing around really fast. The highest energy means that the speed means it's very close to the speed of light. So it can't go faster than the speed of light. So there must be a limit to the total amount of stuff you can pile onto a white dwarf, because if you give it too much energy and too much stuff, the density goes up. As the density goes up, the energy goes up. And eventually some of the electrons will have so much energy that they're almost going the speed of light. And once you get there, it's called a relativistic degenerate gas. And that's what we see at the bottom, which is basically a PDG is a relativistic degenerate gas. And it's to the density of the 4/3 power. So it changes as it goes from a normal degenerate gas to a relativistic degenerate gas. And there's a different constant out front, but notice the mass of the electron has disappeared because it's really small, or at least it becomes, the reciprocal of the electron mass becomes very small as you get closer and closer and closer to the speed of light. Anyway, the relativistic degeneracy then blocks this thing and says there must be a maximum mass. So we can go back to to inform us of what to think about with the ideal gas law, and say if the pressure times the volume equals the self-gravitational pressure, which is what the green arrow is trying to indicate to us, we say the average pressure of a star and the average volume of a star is equal to the self-gravitational energy, which would be gm squared over the radius of the star. The mass of the star squared divided by the radius of the star squared, that minus 1/3 comes from the self-gravitational energy of the entire star on the top of itself. So we can think of the pressure times the volume equals the self-gravitational energy, and we can plug in the degenerate pressure and see what we get. So we then say, okay, fine, degenerate pressure times the volume is proportional to that 1/3 gm squared over r. We can get rid of that constant and muck around with it. We know the volume goes like the radius cubed, and we know the density goes the mass divided by the volume, and we get this really funny number at the end, because all we get is a mass, because we got a relationship between the mass. We can get rid of the volume as a radius, and the radius solves out. It actually drops out because we get a cube of the radius. And the radius disappears, and we find that there is an absolute maximum to the mass of a star when the relativistic degenerate gas becomes the entire self-gravitational total energy of self-gravitation. We find that the maximum mass for a white dwarf is 1.44 solar masses. That's really strange. That's what that latter equation says. It's called the Chandrasekhar limit. And the Chandrasekhar limit basically says that the maximum possible mass for a white dwarf is 1.44 solar masses. And Subramanian Chandrasekhar derived this from Fowler's work a few years prior, who basically found the previous stuff we were talking about, but did not do the relativistic calculation. Subramanian Chandrasekhar in July of 1930 was on board a steamship from India to Cambridge and derived the equation that we just saw above for the relativistic version, and derived the maximum solar mass on his way to go to studies. I think he was 22 or 25 years old when he did this. So above this mass, the electron degeneracy must fail, because then the electrons would have to be traveling at the speed of light. So that gives a prediction for the maximum mass and that's upheld by observation. There is no white dwarf that's ever been observed that is more massive than 1.44 solar masses. And this is described in this little thing. We have non-relativistic Fermi gas, which is the m to the minus 1/3. But if we add in the relativistic terms, meaning it can't go faster than the speed of light, because speed of light, you get the limit of the Chandra X-ray mass, which is 1.44 solar masses. So white dwarfs themselves are the remnant cores of dead stars. And they're stars which were formed from something about less than 8 times the mass of the sun. They're supported against the pressure of their enormous weight. Remember, a typical white dwarf is about as big as the Earth by the electron degeneracy pressure, which is just basically pack the electrons together. And below about 4 solar masses, the principal components of a white dwarf are carbon and oxygen nuclei, and very little helium and hydrogen nuclei on the surface that compose a very, very tiny atmosphere above that. But between 4 and 8 solar masses, they're primarily oxygen, neon, and magnesium white dwarfs. And all of these things are less than 1.44 solar masses. The radius of them are about the size of the Earth, or about 2% that of the Sun. And the densities can be up to 1,000,000 grams per cubic centimeter. So that means you can get 1,000,000 grams of something that's the size of a sugar cube. And the escape speeds are on the order of about 2% the speed of light. Here's the funny thing. All this stuff we were talking about, there's no nuclear fusion anymore. This is the end state of a star. All the nuclear fusion is done. They're not gravitationally contracting either. So there's just residual heat. And where's that residual heat? It lies in the protons and nuclei, the helium nuclei, the carbon and oxygen nuclei, the neon and magnesium nuclei, because they're dodging around between the electrons, among the electrons that are supporting the star from its collapse. So the nuclei are still hot, and they're behaving like a normal gas. They are not degenerate. So they can cool, they're at this incredible temperatures of maybe tens of thousands or hundreds of thousands of degrees, and they behave like a normal hot gas. And they emit light because they're hot, and that's the light that we see from Sirius B, 7 light years away, is the light from the very hot nuclei. The electrons, they never can cool off, they'll never stop that degeneracy, they'll never break that strange brick-like structure of degeneracy. But the nuclei of carbon and oxygen and helium and hydrogen, the very tiny amounts of hydrogen on the surface, will get colder and colder, and that light is that's what we see as the light. Tonight we're going to finish off our discussion about white dwarfs and how they become novae and type 1a supernovae. So once again, we begin with this interesting graphic, which cannot exist in reality, because if a white dwarf were that close to the Earth would be shredded, because a white dwarf is the mass of the Sun, but the size of the Earth. And that actually would have such incredible gravitational tidal forces on the Earth, it would destroy it. But not before the incredible intensity of light from the ultraviolet light fried the Earth, boiled the oceans, and made the atmosphere boil off into space. So lots of things bad would happen if you came near a white dwarf. So let's see what those things can be, because white dwarfs are really interesting things. So we learned last time that white dwarfs are the remnant stars. We've learned over the last couple of lectures, actually, that they're the cores of big stars. Stars less than the mass of the Sun by about 8 times the mass of the Sun. And if those are the cores that the stars that began with less than 8 times the mass of the Sun. The core itself is supported against gravity by electron degeneracy pressure, which we discussed in excruciating detail last time. And if they're smaller than 4 solar masses, the star is. If it begins as less than that, then the end white dwarf is made of carbon and oxygen. But if it's between 4 and 8 solar masses as an initial star, then it becomes an oxygen, neon, magnesium white dwarf, which is much more dense and more massive. We also learned last time that there is a maximum limit to the mass of a white dwarf called the Chandra X-ray limit at 1.44 solar masses. And this is because that if you keep packing mass on top of a white dwarf, it gets smaller and smaller, and the electrons in it have to go faster and faster and faster, and eventually they have enough energy such that their kinetic energy is almost at the speed of light. And once it becomes the speed of light, then that's the limit, and it does bad things, which is what we'll discuss today. And the radius of them is about an Earth radius, or about 2% that of the Sun. The density is over roughly about 1 million grams per cubic centimeter, and the escape speed is about 2% that of the speed of light. So you got to leave them. The important thing is that the white dwarfs themselves, because of the electron degeneracy pressure, do not shine by nuclear fusion or even by gravitational contraction. They're not going to contract anymore. They're staying that same radius forever. So they shine because the protons and helium nuclei and carbon, oxygen, neon, and magnesium nuclei that are inside the white dwarf, those things are still hot, and they would have an equivalent temperature of almost billions of degrees inside. More like tens of millions or hundreds of millions of degrees, but still, that's really hot. And any hot gas glows, and so what we see is the residual heat of those things glowing. The electrons themselves comprise the lattice-like, almost brick-like structure that keeps everything up, and they are effectively at temperature 0. But if they expanded, they'd be very, very hot. But because they're collapsed together by electron in a degenerate state, they are effectively have no temperature. So what it leaves is the nuclei, the nuclei of what were atoms in the center of all the remnant elements. So let's see what happens. As a white dwarf evolves, it will cool. So since it has no energy source, no fusion or anything, it cools off and fades away. And there's a white dwarf cooling sequence on the HR diagram where it starts in the hot upper left and goes to cooler lower right. And eventually they just get dimmer and dimmer. And the eventual state for a lone, solitary, isolated, old white dwarf is called a black dwarf. And a black dwarf will never happen until they take so long to cool off that it would be trillions of years, tens of trillions of years before a white dwarf would become a black dwarf. And the universe is only 13.6 billion years old, so it's not old enough for any black dwarfs to exist. But we're not talking about black holes, we're talking about black dwarfs, which would be old. And those would only happen in the deep, deep, deep future of the universe. They do not exist yet today. So what can exist today as the end result of a white dwarf is a nova. And so novas are stars, traditionally, there's just some star sitting in the sky that all of a sudden flares up extraordinarily suddenly and then dims back down. That's called a nova. And it'll increase in luminosity by, say, 10,000 times, and then it'll fade away slowly. And what exactly is happening with this? Well, in this graph, we're seeing a star, and then afterwards it's very, very bright. And then we see the luminosity has grown up to about 10,000 times the luminosity of the sun, assuming that it was about just a little less than the luminosity of the sun when it started. And this nova state will last tens of days, maybe up to 100 days as it fades away. And then why it's called a nova is that means new star. So, or if you like, it could also be in Spanish, it doesn't go. Well, it actually does go. This is a new star, a nuevo star, and that's another way of looking at it. Now we can think about a more recent star, or an exactual data for a star. This one happened in 2015. This is Nova Sagittarii 2015 number 2. So this would have been the second nova appearing in the constellation Sagittarius in 2015. And as we look at this thing, it got really bright, up to almost, according to some of the measurements, in visual, the purple dots are V, meaning Johnson V, that we discussed earlier on. And that Johnson V magnitude was highly variable, up to a magnitude or 2 over a couple of days, even inside a day or so. And so this was a very variable nova emission that was just visible to binoculars. And over the course of a day or so, it went from 6th magnitude up to 4th magnitude and back and forth very rapidly during its nova outburst time. And then it faded away. It then rather rapidly faded down to 13th magnitude and then came back up. So there must have, this is an interesting element of what we call a nova, and prior to that, it must have been a roughly 13th magnitude. And this data comes from the American Association for Variable Star Observers, and that's the AAVSO.org, and the link across the bottom. Oh my goodness, if you want to go look at it, you can. And I just compared it visual observations, because there were lots of visual observations by people using telescopes and binoculars. It was bright enough to see in binoculars in the constellation Sagittarius. Now, why exactly it has this shape is rather interesting. The strong dip is probably likely due to dust interactions that would have blocked the light, and then finally, once that got dissipated or blown away, then we could see the underlying bright material under it as it brightened back up. So it got as bright as 4th magnitude, then the dusty material that it emitted cooled off rapidly and then was able to, but then needed to be redispersed, that blocked the light and dropped it down to 13th or even 13.5 magnitude, then came back up as the dusty material was dispersed. So there was a lot of emission of stuff that then blocked the light that then we could then see later. So this is what's happening. So a white dwarf that is part of a semi-detached binary system can undergo repeated novas. So we have the white dwarf on the left that's emitting in the nova category. And this artwork is by David Hardy at P-Park. But we have maybe a red giant that's very, very, very close. And as it's close, material, as the red giant expands, the gravitational pull from the white dwarf, which is just as big as or at least not just as big, the gravitational balance point between the white dwarf and the red giant gets to the point where it's more the tipping point towards the white dwarf. And because the two of them are spinning and orbiting each other rapidly, it goes off in this stream-like structure that you see and forms a disk around the white dwarf. And occasionally enough material builds up on the surface of the white dwarf that all of a sudden it explodes catastrophically in a runaway thermonuclear explosion on the surface, because mostly the gas that's falling on it from the red dwarf, from the red giant, would be hydrogen. And so that hydrogen can do thermonuclear fusion on the surface of the white dwarf rapidly and blow material out. Now, if the star is big, then the white dwarf nova can actually blow some of the star away, and that's why we might see, say, what we saw in the previous nova where there was a big blockage. So you could have a bunch of dusty material that then comes off and cools rapidly, blocks the light, then gets blown away by the energy put into it by the nova later. So a white dwarf can be part of that, and so we have the mass. So let's look at it in a diagrammatical format. So we have a main sequence or red giant companion. If it's main sequence, then you get multiple repeated novas, and they're really, really close. So they're semi-detached, meaning their orbital rotation as they orbit their common center of mass. It might take hours or less than a day or so for them to orbit each other. So they're orbiting rather rapidly around each other. And then the mass would, if the matter is on the near side to the white dwarf, is just close, is close enough such that the gravitational pull of the white dwarf is greater than the gravitational pull of the rest of the main sequence companion, then the matter can fall off of there and go towards the white dwarf. So really, these two objects have the same rough mass, or at least comparable masses, and all you have to do is make the main sequence star swell up just enough so that the balance point for the material at the top edges of the main sequence star are just enough so that it can fall towards the white dwarf. So it's like being on a tipping point, and the tipping point is right where the mass transfer stream begins. And once it lands on the accretion disk, there's a hot spot on that accretion disk where the material lands on it, and the accretion disk then goes round and round and round, and eventually accretes onto the white dwarf, which then explodes as a nova. And that's called a dwarf nova. And there's outbursts that have occurred in history. One of the brightest ones, not the one we saw in 2015, but there's been many. There's one a year or so that comes around. There's at least a few a year. That were one in 2015. That was early, and that happened. That was the second one. GK Perseus was a nova in 1901 that occurred and became easily one of the brightest stars in the sky. And we can see the dusty material from this image of that nova that was taken recently by Adam Block at Mount Lemmon Sky Center at University of Arizona, up at Kitt Peak. So This nova then when it occurred, it became extraordinarily bright. How bright is this bright? The American Association of Variable Star Observers has historical data that goes back to 1901 about this object. When it first became visible, it got up to visual magnitude of 0. Visual magnitude of 0 means it was brighter in some places than the planet Venus, or at least Venus was the only thing brighter than it. The Venus, the moon, and the sun were the only things brighter than this star in the sky. So it was incredibly bright. And people really would notice it because that's something that was brighter than every other star in the sky and would come out first at sunset in the constellation of Perseus. And remember, Perseus is very far away from this. Maybe it had to have been relatively nearby the sun because, well, not too far from the sun because look at how easily it was observed. So we have this great, easy observation pattern for GK Perseus. And it grew from about 8th magnitude down, or at least it grew to 0 magnitude, and then dimmed back down rather rapidly to about 12th or 13th magnitude. But now look at what's happening on the right-hand side. That initial nova was because of a huge outburst on the surface of the white dwarf that happened as a result of huge amounts of mass transfer, and that's called a nova event on the left-hand side. But now we get the dwarf nova event because now the stars are closer together as a result of this interaction, because they're semi-detached, and stuff keeps falling down on top of it. So we see these spikes that started happening around the latter part of the 1960s. And we can see the events happening maybe around 1964 is when they started happening again. And the star, the nova is mostly quiescent at a magnitude 13. And every couple of years it does an outburst, and it gets up to like 11th or 10th or even 9th magnitude for a while. And so this has become recently, since the 90s, something that people like to study because dwarf novas are kind of cool. So the American Association of Variable Star Observers, these people love to find stuff, and so you can see all those data points happening with studying this very bright dwarf nova. That's kind of neat in the constellation Perseus. So when it's able to be seen, then we see an outburst, lasts a few days, lasts a few weeks or so, and then it dims back down. So that's where those spikes are as material piles onto the white dwarf, explodes, but then it happens again because as the main sequence star is getting closer, because as this stuff goes out, there's like this dusty, gassy cocoon around both stars, and that provides drag on them, which means that as they orbit each other in that gassy, dusty cocoon, they actually slow down in exactly the same way the International Space Station has to fire its rockets, even though it's 250 miles up from as it orbits the Earth. Every couple of months, it's got to fire its rockets to get above because there's just enough Earth's atmosphere to drag the International Space Station down. So as these two stars orbit each other, there's a lot of gas and dust there, and so they spiral slowly in towards each other. This could be interesting in maybe 10,000 years. Stay awake. All right, so what can happen if you added enough matter? So that we now can see that matter can be transferred from one star to the surface of a white dwarf. What happens if you have a really big one, like that's really close to the Chandrasekhar mass of 1.44 solar masses? Above that, the electron degeneracy pressure we know would fail. So it can't balance the gravity, and so therefore it must collapse. So if you added enough matter, then it would override it. If then the density would rise because there's no way to stop it, because electron degeneracy pressure can't stop it. However, the temperature is not increasing. Eventually, the density gets so incredibly high that the carbon and oxygen nuclei become hot enough on their own to burn and do explosive detonation of nuclear fusion inside of there. And that generates the heat. And then, since there's no pressure to slow the collapse, because the electron degeneracy no longer works, the extra heat leads to more fusion. More fusion means to more heat means more fusion, and so on. And it's a runaway, out of control, catastrophic nuclear explosion, and that makes a huge new supernova type. And that fuses all the light elements in the white dwarf into iron and nickel, and the white dwarf itself gets completely consumed in this explosion, and it forms what we call a type 1a supernova. There's nothing left behind when this happens. The white dwarf completely explodes and is responsible for a huge amount of iron in the universe. So to summarize, we talked about supernova before, but let's look at the two different types. In the top type is the one we're talking about now. We have a binary star that are very close together. One of them turns into a white dwarf in a planetary nebula, and eventually the other one evolves to become a red giant. And that then forms an accretion disk. The white dwarf grows and grows and grows in mass, and eventually it detonates and explodes. We'll compare that to a core collapse supernova, which is what we talked previously, which is an isolated star that fuses hydrogen to helium, helium to carbon, carbon to oxygen, oxygen, neon, magnesium, silicon, and then finally iron. And eventually there's a core, the iron can't withstand it because it takes energy, and then the core collapses. That forms a shock wave at the bottom, which then explodes the core, the star, in a massive explosion. What's interesting in terms of the light, what you see in the sky, is that type 1a supernovae, they're distinct in a couple of ways. One, their light curves, and two, their spectrum. But we can also then remember that there's a huge amount of neutrinos that occur from a core collapse supernova. Remember that from our previous discussion about those kind of supernovae, you get an enormously high density area that produces an enormous amount of neutrons. And that means that the luminosity of the star in neutrinos, not neutrons, but neutrinos now, as a result of these neutron-rich nuclear fusion reactions, the luminosity of the star of a core collapse supernova far exceeds that of the light in neutrinos. So neutrinos are much, much more energy comes out. In fact, more than 99% of all the energy of a core collapse supernova comes out of neutrinos. Whereas with a white dwarf, it's almost all in the light and the kinetic energy. So there's not as much in terms of neutrino impact because of how fast it occurs and what the nuclear fusion is that's occurring. It's happening all inside the entire white dwarf at once. So there's not a lot of time for it to do anything except explode. Whereas with a core collapse supernova, there's the relentless pressure of gravity that pushes it and creates faster and faster reactions. So they create different appearances. So white dwarf supernovas are not the same thing as a core collapse supernova. They don't emit as many neutrinos. But also, white dwarfs' detonations don't have a massive hydrogen envelope. So we have two different kinds of supernovae, and they are distinct by their light curves and their spectra. And if we look at type 1, which are the white dwarf types, which is the purple line, they get really, really bright and then they fade. But type 2 supernovae get really, really bright, have a plateau, and then fade again. And that's because type 2 supernovae, they create all sorts of elements that are much, much, much heavier than iron because of the neutron-rich environment in the core that's occurring as a result of all this. There is no such thing for type 1As, so they just get really bright and then they fade away. The other type 2s are driven by nuclear fission, which is radioactive decay of elements. So that's what the difference is between the two light curves. So then to look again at the process, imagine then you start with two stars as in a binary pair. They're really, really close. They're two normal stars. And then one of them becomes a red giant. As one of them becomes a red giant, then it dumps material onto the secondary star because, well, it's a red giant. And eventually they expand and become engulfed in a common envelope. Once they become a common envelope, because the red giant is done, the core is the white dwarf that's sitting over there, and the other star then gets more massive. So now we've got a white dwarf sitting there with a much more massive common envelope, and then the other star has now been made more massive and therefore burning faster, and that's the yellow star now. And then it spits off the outer layers, but now we've got two stars that are really close, and now the yellow star is a rapidly evolving main sequence star, and the other one is now a white dwarf. Next thing that happens is that then that star becomes an aging red giant star. It starts to swell up even as it exits the main sequence, and then it dumps material onto the white dwarf now, not onto a companion star. And then it reaches the Chandrasekhar limit, it explodes, and either the white dwarf is completely destroyed or the other star somehow survives, but it's still an open set of debate whether or not the companion star actually survives the explosion, but the white dwarf certainly does not survive. So that's the progenitor sequence cartoon for a type 1a supernova. What's interesting is that they all happen as a result of this specific ignition pattern. And I found this, which is really interesting, at the Flash Center for Computational Science at the University of Chicago. So they've done extraordinary computer simulations of what exactly happens inside of a white dwarf detonation. And if it's a gravitationally confined detonation, you get just some nucleus that happens. Some little seed of the reaction happens in one place, deep inside the core of the white dwarf. And when it does, that bursts out, because it's not going to be exactly at the center. It'll be a little bit offset. And because it's a little offset, then it makes a jet. And that jet then plows through the outer material, as we can see, the thermonuclear plume as the reaction is occurring. We get this plume of superheated gas that's occurring in the center, where most of the action is actually happening right at that nucleation point. But the reactions do begin to occur as the density and temperature rises catastrophically in the plume that's growing. Then the plume breaks through the surface, but the white dwarf has 2% the speed of light to escape from it. So this gas cannot escape. So it then goes into orbit around, even as it gets hotter and hotter, and the reaction continues faster and faster. The blue is where it's hottest. And then the plume has to then stay on near the surface, so it scoots around to the other side and forms a secondary plume where it all occurs at once, and that leads to another catastrophic reaction, which now we're going to change the scale and look only at that plume. And that plume then is the thing that goes and destroys the rest of the star completely. So this is a computer simulation that shows the detonation of a white dwarf, and all of this happens within about 1.5 seconds, or maybe 2 seconds. And remember, the original size of white dwarf is about the size of the Earth. So something the size of the Earth all explodes catastrophically all at once. Makes the beginning of Superman's world and Krypton look like nothing. Maybe this was Krypton. Maybe Krypton was actually the surface of a white dwarf. Dun, 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 dun. Don't tell DC Comics. Anyway, so here's the idea behind a type 1a supernova. Dumps on it. Before the explosion, they were separated very tightly. And then after the explosion, a few days later, you got this massive, massive, massive amount of stuff coming off. Probably the original, the contributing star, the big, other main sequence star, probably gets destroyed. We can then debate whether or not it gets destroyed or not. But certainly the material then goes out into space and forms other stars, right? Because that's where we get most of our chemical elements from, is from supernovae events. And so this will form iron, cobalt, nickel, and many other elements that are very heavy, heavier than iron, in a fraction of a second. Well, remember that most white dwarfs are simply carbon, nitrogen, and oxygen, and some magnesium or some neon. So they don't start off with the heavy elements such as silicon and even an iron core. No, that all happens all at once. So when the materials are made inside of the white dwarf catastrophic supernova, those things happen quickly and rapidly, and you don't get that photoionization or the photodisintegration that you find with the core collapse supernova. So you get much of the iron gets created a huge amount of iron gets created in this because, well, that's what you can make, and you don't make anything else, and the iron doesn't have the chance to be destroyed by the energy of the light. So the supernova ejecta then mixes with the interstellar gas. That makes other stars that may use these metals. And remember, astronomers call metals anything with an atomic number greater than helium, and that becomes successive stars. Generations become more metal rich. So everything that we know, all the iron and silicon and phosphorus and carbon and oxygen, comes from exploded dead stars. And all of this must have happened more than 5 billion years ago, prior to the existence of the sun, because we know the Earth is 4.5 billion years old, and we know the sun is 4.567 billion years old. So that's interesting to note that the solar system had to have been formed from gas already enriched by a previous generation of these massive stars. Some of them might have been white dwarfs with the type 1a supernova, and some of them might have been core collapse. Interestingly enough, though, we have a fascinating thing about type 1a supernovae because of the Chandrasekhar limit. They can be used as distance indicators. Now, if we look at this is a supernova that happened in a very distant galaxy in 2002 that was captured by the Hubble Space Telescope. We see this incredibly distant galaxy, and we see a little red dot, and that little red dot is a supernova event that happened in that galaxy. So we can look for the light curve of supernovae in distant galaxies, because if we track them, we see they get brighter, brighter, brighter in a particular curve, a particular light curve, and then they dim out. So type 1a supernovae, because binary stars are more common than massive stars, you don't have to have as massive a star. So type 1a supernovae should be more common than core collapse supernovae, because binary stars are more common, and white dwarfs are more common that are less than 8, where the star begins of the 8 solar mass star. To get a core collapse supernova, you need stars that are 10 or 15 solar masses, and those are really rare. But smaller stars are less rare. So distant galaxies, you'd probably think that they're supernovas type 1a. And here's another example of one that happened in 2002 in the galaxy NGC 1309. And here's one that happened in the Whirlpool Nebula in 2005. There's another one in 1994. And here's one that happened in 2014, in January of 2014. I actually saw this with my own telescope. And that's, as you can see, you just track it around from the days and times. We see that it gets brighter. It starts at magnitude 11, the brightest, and then it gets to its brightest at 11, and then goes back down to 17. So this particular supernova was quite nearby, at 13 million light years away, and we actually use this to help us understand more about that galaxy. And there it is in January of 2014. I took this with the Micro Observatory, which is a free online telescope service, and the supernova is that little star right there. That's in the disk of the galaxy M82. Now, because they all have the same property, that these type 1a supernovae all happen because they have what's called the straw that broke the camel's back. Just when you start increasing the mass above 1.44 solar masses as a white dwarf, therefore they must all get to the same brightness at their peak, because it's the same exact process that creates them. So let's say we measure a whole bunch of these supernovae in distant galaxies. Well, because of the expansion of the universe, which we'll talk about later, the light curves get stretched in time. When you take that effect into account, for all of these supernovae, they have exactly the same light curve. So we know they're all type 1a supernovae because we know this type of light curve for a type 1a supernova. And so we know that all of them get to the same brightness at their peak. And this is a major study of many type 1a supernovae done by Kim et al. Back in 1997, and this is an Astrophysical Journal article. And they looked at how long it took in terms of days, and they looked at the brightness in the B magnitude. So that's a pretty standard brightness in the Johnson B to look for them, because it's nice and broad filter and easy to see these galaxies. Interestingly enough, if we really do a deep survey, such as Rees et al. Did with the Hubble Space Telescope, we see many supernovae. We can see little bright dots in each one of these galaxies, and we see 04 and 05, which is the year in which they did their work. And then we go and look from 2002 to 2005. We see multiple little bright stars embedded inside of each of these galaxies, and we can find example after example after example. And fascinatingly enough, if you use this supernova, because they all get to the same brightness at their peak, you can use them as a standard candle. Just like we can use Cepheid variable stars to get standard candles, we can use type 1a supernovae to get standard candles to these distant galaxies. And in so doing, we can then use this supernova to then measure the expansion of the universe, because that's the last step in order to figure out the expansion of the universe. We can then calibrate to extraordinary distances because they're really bright. We know exactly that they get to the same exact brightness at their peak, and if we can catch them at their peak, then we can then measure the redshift of the galaxy in which they're embedded, and once we do that, we can measure the rate of expansion of the universe because we know exactly how bright they are. So this is an incredibly fortunate thing for this Chandra X-ray limit, because without it, we couldn't do this. So if we look at type 1a supernova on a Hubble diagram, which shows all these dots, these black dots, show that how fast the galaxy is rushing away from us, meaning the distance, and the distance was determined using the type 1a supernovae, and the velocity of recession is what on the y-axis. We then have a Hubble diagram which shows that the farther away an object is, the faster, in megaparsecs, the faster it's rushing away from us. And that line that interpolates it shows the rate of expansion of the universe as measured using type 1a supernovae. And so the Supernova Cosmology Project, there were two major projects that were looking for the expansion rate of the universe using these supernovae. And if we look closely, we find that there's a group that would look for some of them in 1996, and the Supernova Cosmology Project measured the expansion rate of the universe. That's what the red dots are. And measure the brightness of the supernova at its peak for a given redshift. So redshift is left and right, and brightness is up and down. And we can see that the red dots show how bright they were at peak. And if we fit the curve with the best fit curve to this data, we find that the universe is made up of 28% normal matter and dark matter and 72% dark energy according to supernovae. Which is interesting, because this is also done by the High Z Search and the Supernova Cosmology Project. Both determine the same thing and determine that the universe itself is accelerating in its expansion. And that's what we mean by an accelerating expansion. Is that notice most of the dots lie right above it. There's vacuum energy, which is the dark energy. Without dark energy is below. And the average of these things, or the best fit to this data, says that the universe is expanding with some dark energy. So if we actually put this all together, we can then determine the history of the universe as well as its future, and we find that ago the universe was actually rushing away slower than it is today. And that's what those curves mean. The best fit curve says that the universe was expanding slower, and then it started to accelerate in its expansion about 5 billion years ago, and now it's accelerating much, much, much faster as time goes on. And this is a graph by Perlmutter that was used in Physics Today back in 2003 after they discovered this. This led to the team by Perlmutter, the Supernova Cosmology Project, and Brian Schmidt and Adam Rees with the High Z Supernova Search Team. They looked for the expansion of the universe using these type 1a supernovae. In fact, this was one of the main reasons for the launching of the Hubble Space Telescope, was to actually figure out the actual expansion rate of the cosmos. And they used these type 1a supernovae, both of these teams did, in order to discover the expansion rate. And they would be going up to the mountaintops and looking for, trying to get spectra on a supernova that they found using the Hubble Space Telescope just nights before. And then they were hunting for it. And so as one team would leave the scope, the other team would be arriving. So it was an active competition. And it was only because of some miscommunication between members of the team that they have a joint Nobel Prize, because both teams were competing actively with each other. And eventually both teams then discovered that not only was the universe not decelerating in expansion, but it was actually accelerating. So two different teams using different data and different methods of reducing that data, however, both looking at type 1a supernovae, both discovered the expansion rate that the supernova were dimmer than expected. And the reason they were dimmer than expected was because now we're rushing away from them faster than we used to. So that meant the universe is bigger now than expected. Then, therefore, the universe is accelerating. That was the subject of their Nobel Prize award in 2011. So that's our big deal with respect to these white dwarf type stars. White dwarfs, which are really interesting in and of themselves, which form a fascinating end state to stars and form really beautiful things to go observe called novae and dwarf novae. Maybe a dwarf nova. That's why people are looking at that one in Perseus, because maybe a dwarf nova that's bopping itself off every few years, maybe it'll turn into a nearby type 1a supernova. And that's why the interest is that's why there's so many data points of people looking at it, because maybe it'll bop off and become one of these and help us better understand type 1a supernova, which will help us better understand the expansion rate of the cosmos. So it's a very rich area of research, is understanding exactly what detonates a type 1a supernova. This time we're going to be talking about neutron stars and pulsars. These are the massive cores of massive stars after they have died. So this is an amazing set of things. Last time we talked about white dwarfs and what they can turn into. We only said they were the low mass or medium mass stars, but now let's look at the ultra rare type stars and what they do. So once again, let's go back and look at our life cycles of stars thing. We have basically 6 layers that we talked about. At the bottom are the lowest mass stars, which are barely stars at all. They're effectively not even stars because they don't even do nuclear fusion in the core. Those are the brown dwarfs. Red dwarfs are the G and the K and M type dwarf type stars. They just burn for up to 1 trillion years and then eventually become white dwarfs and just fade away into obscurity. Something like the sun, or a little bit more massive the sun, between, say, the sun's mass and up to about 8 solar masses. A sun-like star will live a few billion years. The sun will live 10 billion years. More massive stars live shorter. They become a planetary nebula and make a white dwarf. And if they're in a companion, do a supernova. But now we're going to be talking about the next level up. Much more massive stars. Stars more massive than the sun that then turn into giants and then blue supergiants and then explode into a nova, which we talked about last time, a supernova explosion. And now we're going to see what the remnant is, a neutron star. And that's what we see in this thing. The other 2 things we'll talk about next time. All right, so neutron stars after a type 1 supernova, which is a white dwarf having so much stuff that piles on top of it that it explodes under the Chandra X-ray limit. A type 2 supernova is a supermassive star that gets compressed down into the core, and that core material then becomes a neutron star. And what are neutron stars? They are the remnant cores of supermassive type stars. Well, supermassive meaning about 8 or somewhere between 10 and 20 solar masses as the original star. And when the supernova occurs, there is a bit of a leftover piece. Remember we said in the supernova lecture that there's a core bounce as everything gets to be this incredibly high density down in the core during the supernova. And so this thing that happens is they get compressed so incredibly tensely that we now, instead of having electron degeneracy, which we talked about in a previous lecture, now we have neutron degeneracy. And so this is the same thing as electron degeneracy, except it is done with neutrons. So instead of the electrons holding it all up, and just kind of, and their pressure is no longer dependent on the temperature. Now the neutrons and the electrons and protons merged together to form neutrons, and then those things then support the entire mass of the star. What's left of a stellar core from a star that originally was between 8 and 18 solar masses, the remnant is between 1.2 and about 2 solar masses, but it's really not well known. The radius is about 10 kilometers, which is very small, and the density is enormous, about 10 to the 14th grams per cubic centimeter, which is gargantuan. Funny thing is that something that's that massive, 2 solar masses compressed down to 10 kilometers, the escape speed then is really big, about 70% the speed of light, and it has amazing results. And there's no nuclear fusion happening in this thing, or any gravitational contraction. It is being held up by the neutron degeneracy pressure. It won't contract under gravity anymore because that pressure is holding it up. And there is, even though the effective temperature is extraordinarily high, there is no longer nuclear fusion occurring in it. And so there is residual heat that happen with this thing, and they glow with the residual heat. However, they're really tiny, so their luminosity is incredibly small. How small? Remember, these objects are about the size of the island of Manhattan, about 10 miles or so across, about 10 kilometers across, and say the mass is about 1.5 times the mass of the sun, which is about 10, and that's an incredibly packed object. So, and the escape speed is about 0.7 c, or about 70% the speed of light. So these things are tiny. And they're about 1.3 solar masses. They're incredibly, incredibly dense. If a neutron star were to rest on top of Queens and Long Island, there wouldn't be anything left of the Earth. I mean, nothing. There would be nothing. Couldn't hold it up. The Earth ain't that strong. It would be on the surface of the white dwarf. So if you Google Discovery Channel and look at neutron star colliding Earth, you'll find a crazy, crazy, crazy video on Discovery Channel that shows what happens when a neutron star collides with Earth. Basically, the Earth falls onto the surface and is torn into shreds and becomes a skin only a couple of centimeters thick on the surface of the white dwarf. That's what would become of the Earth if this situation that we see in this image happened. That would be bad. Yet another of the million ways to die in astronomy. All right. So let's talk about the ranges of masses for neutron stars. They range in mass roughly between 1.1 and 3 solar masses. This is not incredibly well known, but that's the observed maximum mass. The theoretical mass is between 1 and 3. But the maximum observed mass is about just a little bit over 2 solar masses. And remember that any compact star smaller than 1.44 solar masses, which is the Chandrasekhar limit, the Chandrasekhar limit is the limit of electron degeneracy as the electrons get closer and closer and closer to the speed of light. And so once the electrons are moving at the speed of light, they can't support it anymore because that's the maximum possible energy that they can have. So then the star is collapsing and collapsing and collapsing, and the electrons are moving faster and faster and faster. So that is the maximum limit that a white dwarf can have. However, if they merge together, they can form a neutron star. Now, if it approaches the Chandrasekhar limit as a white dwarf, it'll explode. But if it collapses under the power of a type 1, type 2 supernova, then it can exceed 1.4 solar masses and go between 1.4 and 3 solar masses, which is called the Tolman-Oppenheimer-Volkoff limit, which is the similar thing to Chandrasekhar limit, except now, instead of electron degeneracy, it is neutron degeneracy. So go back and look at my really long lecture on the nature of electron degeneracy and the previous one on white dwarfs to know what I mean by that. I'm not going to go over that again here. So neutron degeneracy is basically the same thing. It's a similar structure as electron degeneracy, except that the pressure is so high that the protons and electrons merge together to form neutrons, and then that is the link that pushes them all together. So then there if it's above 3 solar masses, then it could be, there are other things that potentially smaller than neutron stars, and the neutrons can have maybe what we call quark stars, where it's not neutron degeneracy that holds it up, but quark degeneracy. And what are quarks? Quarks are the constituents of neutrons and protons. However, there's no objects that are known that could possibly be a quark star, because the maximum observed compact star is about 2.01 solar masses. Beyond 10 solar masses, nothing's going to win. And you have what's called neutron degeneracy pressure. No matter what, will lose, and it will have to collapse to a black hole. So let's see what that works out to be. But neutron stars, when they collapse down to these really, really, really tiny objects, the gravitational field becomes catastrophically large. The field is so big, it's over 200 billion times stronger than the Earth's gravitational field. Well, okay, oops, I made a mistake here. Got a typo. Actually, the typo is that not the star's magnetic field, but the neutron star's gravitational field. It's insanely, insanely powerful, over 200 billion times. Remember, magnetic fields are different than gravitational fields. So if you're just looking at the words, you're going to see I have a mistake. And I'm not going to stop this lecture just because of this mistake. I'm just going to keep going on because here we go. Should have got that at the beginning, but hey, whatever. It's live theater, right? So if the gravitational field is over 200 billion times stronger than the Earth, then nothing could resist the gravitational force of that, and it will be smashed to a complete pulp. And by pulp, I mean all the atoms inside it get ripped apart in very strange ways. So if you had something on the surface of a neutron star, Superman, well, Superman wouldn't even make it, but let's say something was 1 meter above the surface of a 12-kilometer radius neutron star. If you dropped it from a height of 1 meter, by the time it hit the surface of the neutron star, 1 meter down, it would be going 1,400 kilometers per second. But even before it hit the ground, hit the surface, the tidal forces would stretch that thing apart, whatever it is, and would actually turn it into a spaghetti thing. So even if it was something as small as a golf ball, that golf ball would become a spaghetti string, meaning the top of the golf ball would be stretched away from the bottom of the golf ball. And the force or the energy released by that would be greater than all of the nuclear bombs ever exploded on the surface of the Earth in the history of the Earth. In fact, that would be about the same amount of energy that the sun emits in a few minutes, if not more. I should have calculated that. That's a great calculation. In fact, I will leave that as an exercise for the student. But but there's an enormous amount of energy that is put there. So we can say an object dropping inside of this will go to 1,400 kilometers per second. And if you want to have some fun, you can see the kinetic energy of that by saying, well, what would 1 kilogram dropped? If its kinetic energy is the mass times the speed squared, what do you get out of that? What's the total amount of energy? And it's an enormous amount of energy that you get. Anyway, so the time dilation, because of general relativity comes into play, there is actually a time dilation. At the surface of a neutron star, if you had a clock, that clock, if 8 years passed on the surface of the neutron star, yet very, 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 very far away here on Earth, where the gravitational field is much less, or even just like a couple of light years away from the neutron star, 8 years on the surface of the neutron star means 10 years far away from the neutron star, which is very interesting. So there is a time dilation between the surface of the neutron star and far away. So time runs slower on the surface of the neutron star, which is fascinating. There's also gravitational lensing that occurs because the path that light takes as it tries to leave the surface of a neutron star, let's say a little gamma ray gets emitted, if it gets emitted at an angle that's not specifically perpendicular to the surface of the neutron star, it'll start to curve in its path. In fact, what we see in this crazy little image here is what it would look like that if you were at a relatively massive neutron star, you can actually see around the backside of the neutron star because of the bending of the light due to the gravitational field. So each one of these square degrees is 30 square degrees. But you can see past the poles on both sides. So it looks like you can see more. Now, if the radius of the neutron star is actually much smaller, because the mass is higher, then you could actually be at a certain place above the neutron star and see the entire neutron star, the front and back, the entire neutron star in your full field of view, because the light could be possibly trapped in a circular path around it. And that can happen due to gravitational lensing at certain radii, meaning the neutron stars got to be very, very massive. All right, so when you take an object like the sun and compress it down, if you took the sun, a whole solar mass, and compressed it down to something 10 kilometers in size, then you're going to spin it faster. It will spin faster, and that's called the conservation of angular momentum. So angular momentum does get conserved, and so what is angular momentum? Angular momentum is the product of the mass times the radius times the rotation speed, and that's in very, very, very general terms. So if you keep the mass the same, and angular momentum is conserved because there's nothing keep pushing the angular momentum away, so that is conserved for a given mass, radius, and rotation speed. So if that number for the angular momentum stays the same, and the mass stays the same, and you shrink the radius, Therefore, the rotation speed has to go way up. So the period of rotation is going to go faster. It'll get faster and faster and faster as it gets smaller and smaller and smaller. So if you took the sun, which is rotating at the equator every, say, month or so, and if you shrank it to the size of 12 kilometers, it would be spinning about every millisecond or so. And the fastest spinning neutron star is that one with that crazy name, and it rotates about 43,000 revolutions per minute, or 716 times a second. That neutron star is actually spinning faster than a helicopter blade. Helicopters don't spin 700 times a second. They spin a few times a second. They do not spin that fast. So neutron stars, things more massive than the sun, spin faster than helicopter blades. In fact, the linear speed of that neutron star is about a quarter of the speed of light. That's how fast it's rotating. Now, eventually neutron stars do slow down or spin down because they have incredibly strong magnetic fields, and their magnetic fields interact with the interstellar medium. They also can create light as they spin, and that electromagnetic radiation carries away the energy of it, and that allows the magnetic field to interact with it, and therefore carry away the rotational speed or carry away angular momentum by emitting light, which is really interesting. The magnetic field can be so strong it carries away the angular momentum. All right. So now the surface of a neutron star, or even inside a neutron star, is incredibly hot. Remember, they're formed in the forges of supermassive explosions of supernovae. And so we have, when they're formed, they can be formed around almost 1 trillion Kelvin, which is just a catastrophically large number. What is that? We can't even put our hands around that. There's no way to really know what that means. However, they keep emitting neutrinos as they do and as they collapse. And so as even in this temperature, the temperature is so high that that actually induces nuclear reactions that carry away energy by neutrinos. So neutron stars fall very, very, very quickly down to only about 1 million Kelvin, which is still hotter than any other star out there. And what that does is that this lower temperature of 1 million Kelvin means that their peak wavelength of radiation is way out in the X-rays. And that is, if we assume that the neutron star is at the same temperature and that is thermalized, meaning it has a black body spectrum, then we can use the lambda max equals p over t thing that we learned way back, which is Wien's law, and the Stefan-Boltzmann law to determine the luminosity of it given the radius. And we find if we know the peak wavelength out in X-rays, that gives us a very, very, very high temperature, but the radius is insanely small. So that means the luminosity is really tiny. So these things, even though the luminosity should be incredibly bright because of the temperature, the radius more than undoes the effect of that. So the luminosity of these things is very, very, very small. And just to give you an idea, that inset is a graph of, some typical cool stars that are between 3,000 and 6,000 Kelvin. The emission from X-rays would be really huge because they would be in millions of Kelvin, which would make these graphs look like little tiny bumps, and these would look like a tiny bump next to a mountain, which would be how big these bumps would be. But that would be over a small amount of surface area, and the surface area is really small, so the luminosity is tiny. So the temperatures are really hot. Now, here's a really cool thing. When you take something and you make it really small, you have a huge amount of mass, and you compress it into a very small volume, you raise its density. And so the densities of neutron stars are really big, like 10 to the 17th kilograms per square meter, that's insane. It's 100,000 billion times the density of the center of the sun. Okay, that's what 10 to the 14th times the density of the sun means. The sun it's more than 100,000 billion times the density in the center of the sun. Isn't that wild? That's just out of control, which is the same density as an atomic nucleus, roughly speaking. So a neutron star is so dense that 1 teaspoon, which is about the same size as a cube of sugar, would have a mass of the tallest mountain on Earth, all of Mount Everest, all in one place. So take Mount Everest, compress it down to something half the size of a cube of sugar, and you've got the density of a neutron star. Now, that means the pressures are incredibly, incredibly high. Just one last thing about the density. If you go and look at Marvel Comics, shows the character Thor. Thor, the god of thunder, as his hammer is made out of a neutron star. Yeah, that'd be pretty tough to lift unless you were a god. So luckily, Thor's a god, so he can lift a neutron star. But by rights, nothing else can lift it. And somehow, something with that density somehow doesn't do anything when he sets it on a table or puts it on somebody. Yeah, it should have such an incredible gravitational interaction that it pretty much destroys everything around it. So somehow, it can't be lifted by anybody, but yet he can set it down on a table or on the floor of a building. It's really kind of weird. It's just, how can you set it down on anything and have it not go right to the center of that thing? Well, hey, it's comics. What can you say? All right, but that's kind of fun to think. In any event, we can then look at the pressures that happen. And I found a really cool list of pressures. So it's fun to think that 1,000 pascals, where a pascal is a measurement of pressure. So your lung pressure when you breathe is about 1,000 pascals. About 10 times that is heart pressure. About a million pascals, or 1,000 times your lung pressure, is about as hard as you can bite. Or more specifically, if you put a zillion people biting on a nuclear submarine, that's about this pressure that the nuclear submarine's hull can take. And that's the same as a nuclear class submarine can take if it goes down about 500 meters. That's about 1,000,000 pascal. Funny though, is that you can also then take lots of women in stiletto heels and have them all walk on the surface of the submarine. Now, if all these stiletto heels where women were walking such that they all stomped with their stiletto heels so there was no free space on the surface of a submarine, they would crush the submarine because a normal woman in stiletto heels is 10 million pascals. So if many women, so that all their heels were linked together so there was no space between them, all hit the sides of a submarine at once, it'd crush it. Interesting. Power to stiletto heels. So 100 million times the 100 million pascals is the bottom of the Marianas Trench. So really, that's a huge amount of pressure. 10 billion pascals need to make diamonds only 1,000 times more than what is made by women walking in stiletto heels. Fascinating. The pressure of a nuclear bomb is 10 to the 15th pascal, which is 10,000 times what it is at the center of the Earth. 10 times greater than a nuclear bomb is what the center of the sun. Well, now we're getting up to insane numbers. 10 to the 23rd pascal is the center of a Chandrasekhar limit solar mass white dwarf. Chandrasekhar mass white dwarf. 10 to the 31st is the surface of the neutron star, and 10 to the 34th pascals is the core of a neutron star. There's just really nothing to think about these things. It's just very strange. So because remember that the equation of state for materials links density, pressure, and temperature. Under these incredible conditions, there's no way to really get there's no really good state of matter at these densities. So it's all very theoretical, and you have to take into account quantum chromodynamics, general relativity, lots of things in order to actually understand what's going on, the strong nuclear force. And it just is a real mess to try to understand what's happening down there. So the equation of state and exactly how they go is not well known. We don't have it like we have in the previous lecture for white dwarfs approaching the Chandrasekhar limit. All right, so the other thing is that we talked initially about the sun with its magnetic field. Likewise, stars have magnetic fields. So there should be a magnetic field, and so the magnetic field becomes wildly strong as the neutron star collapses. So it's hard to know what magnetic field kind of strengths are, but the fun thing is we can say the 32 micro Tesla. So the Tesla is a unit of magnetic field. and it's the SI unit of magnetic field. So 32 microtesla is the strength of the Earth's magnetic field. So if you pull out a compass and just say what's north, that's why you have to have a very, very balanced thing, because it can get messed up by other magnetic fields around you. And if you bring a refrigerator magnet next to it, which is 5 millitesla, which is 100 times stronger than the Earth's magnetic field, then a typical compass will point at it. So that's 5 millitesla. And the sunspots on the surface of the sun are about 0.3 of a Tesla. And those things actually serve to show you the Zeeman effect, which actually can be measured. So that's actually a pretty strong magnetic field, is 0.3 of a Tesla. Then the very strong, like 1.25 Tesla, is what you have with very strong magnets that you can buy, say, off of Amazon, 1.25. And if you go and buy, like take apart a loudspeaker, like a big audio loudspeaker, and then look at the coil gap that they have inside the gap, that's even stronger. Again, it's about 2 Tesla. If you go get MRI at a lab, you're going to be experiencing about a 3 Tesla thing, and some of those can go up to 17 Tesla. The Large Hadron Collider has magnets that are about 8 Tesla, and those things serve to confine extraordinarily hot plasmas, and they can bend the paths of protons and electrons going at nearly the speed of light. That's what 8 Tesla can do, and they're some of the strongest magnets known. But the ITER experiment, which its goal is to try to instantiate nuclear fusion, and that's what the superconducting magnet system is for ITER. Those are only 13 meg Tesla. 16 is kind of a funny thing. There's some really funny videos about you can levitate a frog with 16 Tesla. And the water molecules will actually align and then go against the magnetic field, and that makes the frog float. So have some fun. Google floating magnetic frog, and you'll see some funny videos. A little bit stronger than that is our experimental magnetic resonance imaging, which is the strongest strongest superconductor in the lab. And the maximum strength for short period magnets is about 27, and 45 is continuous. 100 is the surface of a white dwarf. But neutron stars have 10,000 to 100 million Tesla. There is literally nothing else out there that does this thing. That the sun can't do it. White dwarfs can't do it. Nothing can do this except neutron stars. And magnetars, which are supremely magnetic neutron stars, are between 100 million and 10 billion Tesla. Now, if we then say, wow, how big is this magnetic field? If we took a magnetar at the top end of that range, which is, say, 100 billion Tesla, and that neutron star passed within the orbit of Pluto, that would demagnetize every hard drive on Earth at 40 astronomical units. That would be a bad day. So, yeah, these things are insane, insane magnets. So they would have visible effects on the solar system at 1 light year away, a magnetar would. So if they got really close, it would be bad. So let's look at those things. These things are really, really, really bad. So let's say the magnetars are incredibly strong, and they are possibly the sources of particular gamma ray bursts called soft gamma ray repeaters or anomalous X-ray pulsars. So what's happening with these magnetic fields that become that strong? The magnetic fields can be so incredibly strong that the energy density inside the magnetic field is larger than is required of ordinary matter. So we can say, what is E equals mc squared for a proton? What is E equals mc squared for an electron? And the magnetic field itself in space exceeds that of the energy of an electron and proton in mass. And what it can do is that the magnetic field can polarize the vacuum. In fact, the vacuum of space itself then becomes polarized by the magnetic field, and the space itself becomes what's called birefringent. And birefringent means that space itself has multiple ways that it can refract light. So go back and look at our refraction. We think of a refracting telescope. It refracts the light. It changes the direction. So when it's birefringent, it depends on the polarization of the light, and depending on the polarization of the light, a photon can be split apart, and the light can be split apart or forced to merge. And if photons can be forced to merge, then they can create particle-antiparticle pairs, such as protons and antiprotons, or electrons and anti-electrons, which is really crazy. Once those things are created, then those proton-antiproton pairs can then recollide and form gamma rays. Also, such strong magnetic fields take atoms and they force the atoms to become, instead of spheres, the atomic radii become cylinders or needles. So atoms as they exist around us cannot exist because we think of atoms as having that nice little Bohr radius where it's like electrons are zipping around in like spherical distributions or radial distributions. No, they become cylinders, which is very, very, very strange. So atoms can't exist, or chemistry that we know it can't exist near neutron stars. So molecules themselves melt close to neutron stars because of the reshaping of atomic structure. So that means that the magnetic fields themselves become so very strong that they actually stress the crust of a neutron star and fracture it. So remember, the density is incredibly high, but that's enough to actually push the nuclei apart because they're being deformed, and they stress and fracture them. That makes a star quake, which then emits huge amounts of gamma rays. Those gamma rays then make a fireball, which then get trapped by the magnetic field. And that trapped magnetic field, then the light becomes trapped, and as the star rotates, becomes a burst of gamma ray burst, or a millisecond gamma ray burst. So you get these whips of things that you have of a series of gamma ray bursts that go bip, 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 in many times in milliseconds. So as it comes in and out of view as it rotates. So these things last only a few seconds and have been observed by the Fermi Gamma Ray Telescope as well as the Swift Observatory as well. So magnetars are the most powerful magnetic field in the cosmos. So once again, we talked about the equation of state, and like we said before, you don't get this. It's just like we have before. We have the ideal gas law, which relates to pressure, density, and temperature. No, that's not. You can't have that on your neutron star. And what about the relativistic electron degeneracy pressure? Nope, you don't get that either. There's something else going on inside of neutron stars. In fact, the study of neutron stars and their equation of state is an active area of research. And nobody really knows exactly what the equation of state is, because you have to take into account many, many things, such as general relativity, quantum chromodynamics, superconductivity, superfluidity of matter. And you can't even make these materials on Earth. I mean, it's impossible. So the only way to observe them is by finding things, but those things are hundreds of parsecs or thousands of parsecs away. So the equation of state is strongly dependent upon the size and observed temperature of a neutron star and rotation rate. So one of the important things that astronomers can do to understand neutron stars is simply find the radius of a neutron star. And there's not many that are close, but there is one that is very close, that's relatively close, that people keep trying to study in order to get it, and we'll get to that soon. So the structure of a neutron star inside, remember we talked about the sun, it has a core structure and so forth. But the structure of a neutron star is really fascinating because this thing's only a couple miles, it's only 10 miles across. So what does it kind of do? Well, with these incredible densities, we get this very strange crust. And the crust, it's a solid. This thing is a star that is a solid. And the surface is basically an iron-nickel solid at the crust, which is about just a half a kilometer thick. And it is a thick crystalline iron nucleus crust with electrons that go around. So you get just basically a hot ionized gas of 1,000,000 Kelvin. And it's a hot ionized gas that's a solid, which is really weird to think. Is it a gas? Is it a crust? What is it? It's kind of a weird thing. Inside of there is an inner crust of electrons and neutrons about a kilometer or so thick. And then there's an outer core and an inner weird core. And there should be these weird superconducting states. But recently, in 2017, there was a fascinating study that actually kind of got at what these states can really look like. So the surface of the neutron star is an ocean of ions or a crystalline crust. The ocean would be an electron gas with a crust of ions across it. And then the outer crust would be a crystal of iron and silicon nuclei with an electron gas. Remember, the electrons stay a gas, but where the nuclei would be thick. And then the inner crust would be more neutron rich. And then you get this weird phase called nuclear pasta. And it's not some flying spaghetti monster thing. We'll talk about that in a second. But inside, between the crust where it's actually nuclei, inside in the core, there are no longer any nuclei. It's just so dense that nuclei don't even exist, and you just simply have one big nucleus. So the inner 9 kilometers is essentially a uniform nuclear matter, where it's just a sea of touching protons and neutrons, mostly neutrons and electrons. So that's what's interesting. But what do we mean by this nuclear pasta thing? And this was a study done by Kaplan and Horowitz. It was shown in the Review of Modern Physics in 2007. And there's the link in the archive before, but I'll get to it a little bit more. So what happens is that there's a slice through it, and so the outer crust is neutrons and electrons, and the inner crust is nuclei and electrons, and then the inner crust is neutrons, electrons, and nuclei. And then the outer core, you don't have any nuclei anymore. It's just neutrons, protons, electrons, and muons. And then you have weird stuff, exotic phases in the inner core. But there's a very strange thing that happens in the green middle region right in there. It's called nuclear pasta. And where it actually goes to this very, very strange phase where you have, let's say, in the inner crust, which is that upper level, but between the mantle and the inner crust, you start with these pure neutron fluid, which is the greenish area, and you have a neutron-proton superfluid. So you have pure neutrons moving around, and then a neutron-proton fluid that's in the yellow dots. And eventually those things become larger and larger because the proton-neutron fluid has to actually get pushed together at higher and higher densities. Eventually the neutrons and protons become stretched into a pasta-like phase, such that you have just neutrons and protons in like tubes, and that's their phase. So it's like an atomic nucleus in the form of a cannoli, or a pasta, or a mastoci, or a ziti. And deeper in, the nuclei then form sheets, like lasagna sheets of nuclei. So you have an atomic nucleus in the form of a lasagna pasta. And deeper in, you start to swap it out, and it becomes pure neutrons in the core, and with some isolated protons. But then eventually you don't get any more isolated protons because the density is too high for individual protons and electrons to exist, and they're forced into neutrons. So it flips, and you have pasta, a lasagna pasta of just pure neutrons, and then it becomes a pasta of cannoli, of inverted pasta, where then you eventually get down to a pure fluid of neutrons and protons in the core. So you have these really strange states, very, very, very strange states. And they go into exactly how they look and how they shape. And it's a fascinating article that I invite you to go to. And hit that Astrobytes article that I put on the link there. It shows you what the various things look like. But basically, the nuclei deform. They're no longer nuclei. The strong nuclear force has very strange behavior in these densities. And the individual protons and neutrons bind together not as spherical nuclei, but as spaghetti or waffle or lasagna type nuclei. So we no longer have anything that looks like, oh, this nuclei with next to that nucleus. No, the nuclei are basically huge numbers of protons and neutrons that form spaghetti and waffle type structures or lasagna type structures, which is really strange. And so then we get this strange of appearance of a neutron star itself, and where you have this tiny atmosphere, a crust and an inner crust, and who knows what's going down in the core as the neutrons and everything break down to become quarks and individual quark things. And Neutron stars are really hairy as the end thing. Nobody really knows what's going on inside of them. They're incredibly hairy objects, but they're the most exotic possible state of matter in the cosmos. Black holes are really simple, as we'll see next time, but neutron stars are incredibly hairy. This time we're continuing our study of neutron stars and seeing how we actually observe neutron stars, because they're really tiny. So how do we even know they exist? And that's the real question on today. And that's what we're going to talk about, is how we know neutron stars exist. And they're known by the name of pulsars. So let's go back and again look at what we learned from a neutron star last time, which was it's really small, it's really dense, it's kind of like an atomic nucleus all on its own. The magnetic field is extraordinarily large, and the escape speed is nearly the speed of light. Light bends around it, and if you drop something from a meter above it, it will hit the ground with an explosion that would be the equivalent of many nuclear bombs. So yeah, these are extreme objects, and deep in the core they might be quark-type states. There's these weird pasta-like states, and it's very strange. And they're forged in the moments of an enormous explosion called a Type II supernova. All right, so let's look at how they were discovered. They were discovered by accident in 1967 when Jocelyn Bell, who was a grad student under Anthony Hewish, who was her advisor, and they were looking for very rapidly pulsating radio sources. And what they were doing is they were hunting for oscillations in the solar wind. So their study was the solar wind. So they set up a series of radio antenna arrays on a big field and watched as the sun went overhead, and they watched the sky to see what the scintillations were at radio frequencies. And so they were looking for very short period variations, because they're looking for scintillation due to the solar wind. And so they were taking really fast samples and trying to actually do a big amplification on top, because it's basically a big radio amplifier. And what they found that something was pulsing. So they found a pulsar that was pulsing at about a millisecond, or 1 millisecond long pulses. These tiny pulses once every second or so, and a very repeated rate. And what happened was that they just thought this was an amazing object. And Anthony Hewish, Jocelyn Bell actually discovered it, she was pouring through the data, and the reason she discovered it is because they left the array running overnight, and when the sun wasn't in the sky, they found something that was doing this pulsing, this regular pulsing in the sky. And in fact, the technology for it existed, but just nobody had ever done this kind of study before, so they didn't know what they'd found. So she did the analysis, she made the discovery, but because she was a graduate student under Dr. Hewish, who was running the entire experiment, he got the Nobel Prize and she did not. Now, this is an interesting little case study in the nature of things, but really even Jocelyn Bell herself said, look, this wasn't worthy of a Nobel Prize for me to get. And in fact, she said that later on, after he won the Nobel Prize, that the point is that he would get all the blame if it fell apart. So he gets all the blame, so he gets all the credit. And there were just people working under him. It's not like it was her idea to start the entire project, it was his. So, but yet still people always still remember Jocelyn Bell as the graduate student that got passed over for a Nobel Prize. Anyway, her discovery and subsequent confirmation by others showed that there were these radio pulses that occurred in very short pulses on extremely repeatable rates. So what they discovered is that this could actually be explained by a pulsar, and they called them pulsars. And the thing is that they said, well, so we explained this by saying they're rapidly spinning magnetized neutron stars. And so they're the magnetic field. So they actually tried to determine what the heck these pulses were. And they said, well, we've learned about variable stars, so they could say, could it be a star that's pulsing really fast, like in and out, like getting bigger and smaller, so it would do these pulses. And there would be no known mechanism for it to actually collapse back down. And so they thought of many other possibilities, maybe it's a fast-rotating planet, or maybe a fast-moving object, or maybe little green men. That was one of the initial ideas, was that, wow, maybe it's an alien signal, but when they found others, they said, nope, it ain't that. So they actually tried to figure out what it could possibly be, and they said, well, what if it's actually a rotating star with a hot spot? And they thought, well, this is extremely bright, extremely fast rotation, and they determined that that an object that was very distant enough to actually glow in this type of way, and emit the kind of radiation that they found, it would have to fly apart in order to, the object would spin itself apart. So there was no known astronomical object other than a neutron star that could actually hold itself together and spin once every millisecond, which is what they found later, is that they're millisecond pulsars. So maybe 10 times or 100 times a second, or tens of times, or maybe a few times a second. And the only thing it could hold itself together was a neutron star. Everything else would literally fly apart. And so what you have is the model of such a spinning object is you have a very strong magnetic field, and the magnetic field creates beams of radiation as the electrons themselves spiral around in the magnetic field and are accelerated from the surface of the neutron star all the way out along the magnetic field. And as they do so, those hotspots then become beams because the electrons then emit their radiation because of synchrotron radiation, which we talked about previously. And synchrotron radiation means that they are spiraling at nearly the speed of light in an extraordinarily strong magnetic field. And so that is beamed, and so these become beams. And the magnetic field does not have to be aligned with the spin axis, just in the same way the Earth's rotation axis is not aligned with its magnetic field axis. In the same way a neutron star's magnetic field is not necessarily aligned with its spin axis. So if we're in the direction of one of these beams, then we see a blip. If we're not in the direction of the beam, then we don't see a blip, and that's that. So this particular thing would create enormous bright spots in optical, radio, X-ray, and gamma ray. It would spin. It would make light in all of them. So what we find is here's a better axis, better concept of it. So the magnetic field lines are attached to or are part of the neutron star. The spin axis is up and down. The equatorial plane goes left and right. And the magnetic field is misaligned. So the red arrows demonstrate the radiation that's coming from both the hotspot as well as the electrons and even ions are spiraling in the magnetic field at nearly the speed of light and emitting synchrotron radiation. It is thought that the magnetic field would be so strong at the surface of the neutron star at those hotspots that it actually lifts the electrons off of there, and the act of lifting that releases energy in the form of light. Now you'll notice that the neutron star can spin pretty fast, like milliseconds, and some of them, as we saw in the last episode, can spin maybe a quarter of the speed of light. But that means the magnetic field has to spin that fast. And so the magnetic field itself, at the edge and the boundaries, there must be some boundary where the magnetic field, the tips of the magnetic field away on the equatorial plane, are going around at the speed of light. Because if it's fixed in there, those magnetic fields don't get dragged. They're kind of like, it's the field lines. They move with it, so they must rotate. So at some point, the magnetic field must rotate around at the speed of light. And that's where the pulsar becomes a wind, because now the magnetic field breaks down, and then the electrons and things can spiral out along those wind-like lines going left and right, or along the equator of it. And that can fling electrons out at nearly the speed of light, and ions out nearly the speed of light on unconnected magnetic field lines. So the magnetic field is very strong nearby, and it's a very disruptive magnetic field nearby. Just like we talked about the sun with the solar wind, this is just that on ultra 10 to the 15th, 10 to the 30th steroids. That's what that is. So the hot spots are where the electrons get lifted because of the strong magnetic field. They emit light, and they also spiral in the magnetic field and form the beams of radiation that we see as a lighthouse. And so here's an example of a pulsar that has its magnetic field rotating, and so the beams are coming out of the hot spots. And so what we're going to do is we're going to follow it as it rotates faster and faster. The electrons trace out the field lines as they spiral around, and emit light as synchrotron radiation. But the neutron star itself is hot. Remember, it's about 1,000,000 Kelvin, so it's insanely bright. And now as it passes in our direction, we see a bright spot, a pulse of light that comes from the pulsar, but only if we're right in the line of that. And I'm sorry if that triggered anybody. Maybe somebody's got some kind of crazy thing going on where they can't actually look at that stuff, but we see that the magnetic field is an integral part of the pulsar model. And so there's our picture, a much more artistic rendition with the electrons spiraling on the blue magnetic fields, but really the magnetic field wouldn't be like blue like this. It would be a cloud, that would be a real mixed up cloud that would almost be rigid. You would actually expect the total energy density in that to be so strong, and how much material would be cruising along in it, that those field lines would actually feel rigid. They would hit you, and they would actually have, so if you were there, another one of the next million ways to die, is that if the field line smacked into you, you would be whacked and sent along in a very, very, in quite a pitch into the cosmos as it smacked into you. So those magnetic field lines look gossamer, but they would actually be almost solid. That's an interesting thought. So here's another version of what we would see, maybe the effect of a pulsar on a supernova remnant. Remember, these are formed as a result of a type 2 supernova as a supermassive star explodes. And so the pulsar itself, as it rotates around, generates an enormous magnetic field. The beams of light carry huge amounts of gamma rays. The gamma rays then illuminate and excite the material around them, causing the supernova remnant to glow. So many of the supernova remnants that we see, and what we'll talk about later, actually are glowing as a result of the magnetic field energy that's being pumped into them from this tiny, tiny, tiny source. So the supernova remnant that we see there might actually be a light year or two in size. And remember, and a light year is 10 to the 13th meters, right? But the neutron star is only about 10 or so kilometers. So that dot that's in there is actually completely invisible. Actually, it's not invisible because it's extremely hot, so it's emitting X-rays and optical light. So we get this tiny, tiny, tiny thing that's exceedingly hot and emitting huge amounts of light and energy. All right, so because they do that, pulsars evolve. And we don't see them, of course, if their jets aren't pointing our way. And pulsars will radiate their energy away very rapidly. And that's because the magnetic field will cause the light to occur. And if it's emitting light, it's losing energy. If it's losing energy, then it must slow down because basically this is one big dynamo. And so we can think of it as in just the same way as how do you get power out of an hydroelectric dam? Well, you basically put a whole bunch of magnetic turbines, and the turbines that the water flows over are bar magnets. And so you just spin the bar magnets, and if you spin a bar magnet, you generate electric current. When you generate an electric current, that makes that hot spot in the neutron star. That's what we see. This is generated current from from a dynamo effect. But then the dynamo effect creates electricity. So literally the water imparts some of its energy into the fan, well, it imparts a significant amount of energy into the paddles that it goes down through a hydroelectric dam, and it spins those things up really fast. And so basically we convert gravitational energy, potential energy, into electricity. And that's how a hydroelectric dam works. And that makes the water fall slower after it goes down the dam and across those things. In just the same way, the energy that is released by the pulsar as it spins means the pulsars spin slower as they age, as they lose rotational energy. When they're young, they're fast, and they're old, they're slow. And so if they're slow, they don't do the pulsing dance, and they don't have as strong a magnetic field. That starts to weaken. And that they still could have an incredibly strong magnetic field, but there's no rotational energy left in order to drive a dynamo effect. So older supernova remnants are almost undetectable. However, they're found all over the sky, and this is from the Fermi Space Telescope looking in gamma rays. And so these are radio pulsars found that are part of the Fermi unidentified sources. So Fermi Space Telescope goes out and looks for gamma ray sources, and what we can do then is collate those gamma ray sources with radio sources, and that's what's been done here. And all those little circles are discovered pulsars inside of from the gamma ray sources from Fermi Gamma Ray Telescope in the sky. So this is an all-sky view showing a series of discovered locations in the sky for pulsars. So they emit both gamma rays and radio, as well as optical light as well. Again, as they get older and older, they get cooler and cooler. And so when you have isolated neutron stars, which they will be after time, because the supernova remnant that came out of them as they exploded spreads out into space, seeding other stars, helping clouds make planets and things. But the neutron star gets left behind. It's all by itself. And sometimes you can actually there's maybe a chance that one can actually see them. And so this is an isolated neutron star found by the Hubble Space Telescope, and looking at it with also a couple of extreme ultraviolet explorer, which it looks in UV, and X-ray from ROSAT to actually confirm, yes, this actually is a pulsar, and trying to figure out how far this one is. Now, getting the distance to something would allow, and knowing its brightness would be able to get you the size. So this is pretty good that it's in front of some molecular cloud that's about 400 light years away. So it's got to be closer than that. And yet it's incredibly, incredibly hot because it's emitting mostly in the X-rays. And it's really, really, really small because it's so dim. So if it's 25th magnitude visual in visible light, which is almost on the boundary of what Hubble Space Telescope can actually find, and it's less than 400 light years away, it has to be insanely small, about a few miles across, in order for it to actually be visible to us. So any isolated neutron star that we would actually be able to see in X-rays and optical light is actually relatively nearby, which leads us to think that there's probably hundreds of millions of these neutron stars orbiting the Milky Way, because there's a lot of metals, meaning gold, nickel, iron, and other heavy elements all up and down the periodic table that were produced in supernovae. So there has to be a lot of these things. Luckily, the Milky Way is really big, and these things aren't necessarily ever going to come into the space of the solar system. And the Earth is 4.5 billion years old, and the chances that a neutron star will pass inside the solar system are practically zero. So we're probably safe, even though there's hundreds of millions of these things out there. That's wild thought. That even that is nothing. And so as one looks at the size scales of the cosmos, that makes more sense. But this gives you an example of just like, well, these things are really so far away that we would never actually encounter them. All right, so can we actually encounter a supernova or a neutron star? And the answer is kind of. And in history, we did talk about some supernovae in the past. On July 4th, 1054, a new star appeared in the sky. It was brighter than Venus for almost about 2 years, almost 2 years, and was even seen by the Anasazi. So on the right, we see what the vision is from Chaco Canyon, and then a glyph from ancient Chinese astrologers who way back in 1054 also documented it. There are other documents as well, but these are cool pictures I chose to show to you. And the Crab Nebula kind of looks like this. On the bottom, that's today's view of the Crab Nebula supernova remnant, and in the center of it is a pulsar, and we see the image of it pulsing above. And that pulse is happening, this is happening faster than that, but we're actually looking at it in an optical light or infrared light, so we can actually get a picture of it. And that means we're kind of looking at it in a kind of strange way. You know how you can kind of see a helicopter blade going backwards if you flash a strobe at it? Or if you have something moving in a circle really fast, you hear a strobe at it, or just look at it with an overhead fluorescent light bulb, which has that buzzing sound that makes a definite flicker. So the flickering allows you to see it. So this imaging says we take a series of pictures rapidly in sequence with a definite space between them, and hope we can catch these things. So this was actually caught, and it actually does have that double pulse. So there is actually a two-pulse for this neutron star in the center of the Crab Nebula. Now, the Crab Nebula itself is emitting huge amounts of X-rays and gamma rays, and it is the brightest X-ray source in the sky. In fact, when people talk about X-ray sources, or they say they've actually measured in terms of crabs. So how many, is it a millicrab source? Is it a microcrab source? Is it a demi-crab source? Because the Crab Nebula is the brightest thing in the sky. And so every other X-ray source can be measured in terms of how bright is it compared to the crab. That's kind of an interesting way of thinking about it. So the Crab Nebula is the brightest object in the sky in X-rays. And it's located pretty close at about 6,500 light years away. And the diameter of that whole thing is about 11 light years. So this one little neutron star, a neutron star that's only about 10 miles in diameter, is actually pumping out so much energy that it can illuminate and cause to glow an enormous cloud of expanding gas that's from the shredded supernova of that star back in 1054. And the speed it's going is almost 1,500 kilometers per second. So this has actually been measured to actually go to actually see the motion. So Hubble Space Telescope keeps revisiting the Crab Nebula, and we can see the clouds move with time. And we see also that the Crab Nebula can be measured at going about 30 times a second. So that's really fast to have something really small rotating that quickly. And this is interesting, this Crab Nebula image, because if we go then look at multi-wavelength versions, we took the image that we had before and we call it a different color. So now we're mixing 3 different colors of light. And the yellow wispiness that we saw is the image that we just saw, just converted into black and white and then colored yellow. The red sort of ambient glow is infrared light from dusty material. And then the purplish glow in the center is due to X-rays, and that's the X-ray emission, that purplish glow in the center, which actually seems to have a slightly different structure. But it even seems to be pushing these cavities around. So you can see the X-ray glow seems to be pushing cavities around and making bubbles and holes. And this combines the X-ray data in blue is from the Chandra X-ray Telescope, and the red is from the Spitzer Infrared Space Telescope, and of course the yellow is the Hubble Space Telescope. Now the neutron stars, we saw from the lighthouse model that it's creating this enormous magnetic field which is shooting particles out all over the place. And let's see what that actually looks like. Because the Crab Nebula itself, that central region that's glowing in X-rays, has a central disk and a couple of jets. And there's like this twisty jet that's coming from the center, and that bright dot right in the center, that's the neutron star. And we can actually get a picture of this with the Hubble Space Telescope. Now the Crab Nebula itself is a very, very tiny image in the sky, and this is a tinier yet image. It's only a few. It's only a few tens of arc seconds across, but still. What we see is that there's this wispy type of structure, and they're merging to form these rings. So there's an inner ring that's glowing and an outer ring that's glowing. And those 2 rings are material that's being flung out at nearly the speed of light into the outer ring. And so that's causing enormous motion. So there's and this has an animation, which the Chandra group has actually created for us. So the Chandra X-ray Telescope has been observing it over many years and actually can see the motion of it. So this is just zooming in because you can just like zoom in, just like you zoom in when you try to look at a picture on your phone or something. So just zooming in, so we can see the waves of material moving away from the neutron star and along the jet. So material is coming out of that neutron star from the surface of it. The equatorial region where the pulsar's magnetic field is approaching the speed of light flings material out at nearly the speed of light, and it slams into the materials on the side, emitting huge amounts of X-rays. So most of the X-rays in that cloudy structure happen because of electrons and ions that have been accelerated to nearly the speed of light, And as they collide with other things, they shock heat the gas to X-rays and emit X-rays. The rest of it is due to extraordinarily powerful magnetic fields that occur inside of there. So there is a huge voltage difference that occurs because of the strong magnetic field, and that's the thing that accelerates the electrons off of the surface. And by that huge voltage difference actually releases an enormous amount of energy as they're pulled off of the surface of the neutron star, because they have to overcome the pull of gravity. So the magnetic field is creating a voltage difference. The voltage difference overcomes the pull of gravity, and in so doing releases light, because that's how it has to. That's the releasing of energy in that particular fashion. So we get these polar jets that occur that come from the north and south pole that are not because of the rotation axis of the magnetic field. The magnetic field is making those waves. All right. So I invite you to go take a look at that, because that's really cool, because that actually shows movement of something that's 6,500 light years away, which is just wild to think. And here is a view, a more recent image from the Hubble Space Telescope of the Crab Nebula. And you can definitely see the pulsar definitely smack in the center. We can see the wispy, cloudy structures that occur because of the vast magnetic field permeating this entire thing. And if you got within a light year of that thing, it would completely wipe out the hard drives of any computing facility there. And if you got within an astronomical unit of it, it would tear everything apart. Because, well, no, it's still a solar mass, but if you got within, say, a couple of radii from it, it would definitely rip everything apart there. So you don't want to get very close to that, because that cloudy structure is permeated with a stronger magnetic field than can be made on Earth. And you can still see the wispy structure of the jet-like material that comes out that makes a dusty jet that looks kind of like a dark tendril that points away from the pulsar. And so you've got a bright inner ring. That inner ring is where the light is being generated by shock heating and forming X-rays. That X-rays then, and this is a Hubble image, invisible light. The X-rays then step down as they interact with the material in the cloud to make it glow, and the ions then cruise through this very complex magnetic field that permeates the whole thing as the unclosed magnetic field lines try to recombine, even as the shock waves itself push the entire nebula apart. So the study of the Crab Nebula is the thing that you do if you want to learn pulsars and neutron stars, because it is the nearest neutron star that's doing major activity. And in fact, the Crab Nebula, as Messier object number 1, is an easy target in small telescopes. And you can actually see this thing in an 8-inch telescope from a dark location on Earth. So that's really interesting to think that that's something that happened there can be seen so easily. Well, let's look at other ones. So about 11,000 years ago, there was another supernova, the Vela, that in the constellation Vela exploded. And we see that wispy sort of bubbly structure that's in the middle, not the bright spherical pink in the up top, and not the bright yellow reddish in the upper left, but no, the wispy bubbly stuff that kind of looks foamy in the middle. And not the blue thing at the top. That's just an internal reflection of the telescope from the digital sky survey. So that is the remnant supernova remnant from the pulsar that created this thing. And so the Vela pulsar is part of this. And those outer layers crash into the interstellar medium. And you can see there's a lot of gas and dust in this area. And as that material crashes into it, it shock heats it and makes it glow. So material is just completely hitting all of this stuff. And it was exploded about 11,000 years ago, and as the material crashes into other stuff, it makes it glow. And that's where that glow comes from. And this image that we see spans almost about 100 light years, and the object itself is about the diameter, and this is about 20 times the diameter of the full moon. So this is a big composite image from the digital sky survey, which is an amazing piece of work by David DeMartin at Sky Factory. It's a fantastic piece of work. So What's fascinating is that, in my feeling, is that 11,000 years ago was when the first structures were being built on Earth. In fact, the first human structure was Göbekli Tepe, and that was built about 9,000 BC, which corresponds to roughly when this thing went off. And it would have been visible from Turkey, where Göbekli Tepe was built. So perhaps 11,000 years ago, the first people saw this bright star in the sky, and somebody said, "That's a god, and I'm going to make it one. So build this big temple." So go take a look at what that is. Anyway, so the Vela Pulsar is something that is actually seen in the sky. When we look at it, it's about 1,000. It's about 1,000 light years away. It's nearer than the other. It's about 12 miles across. So this is actually nearer than the Crab Nebula. Actually, it's a slower rotating pulsar. It's about 89 milliseconds, but still, that thing is rotating faster than a helicopter. And there's a jet in the center that's moving about 70% the speed of light. And we're going to look at some Chandra X-ray data from the summer of 2011. As it zooms in on the center of the Vela Pulsar, we see the Chandra data in blue in the center, so it's going to get rid of the optical view that we see, just showing us the Vela Pulsar in X-ray light. Now, the Vela Pulsar itself is also deeply studied by Chandra, so now we're going to zoom in on the central pulsar that created the supernova remnant we saw, and that thing actually moves over time. So there's a central object, and there we see the motion of the Vela Pulsar. We see the jets moving out at approximately 70% the speed of light. The pulsar is deep in the center, and we see the material rocketing away from the disk that makes it. So there's kind of a bent sort of appearance of a disc-like structure. That's the material coming off of the rotation axis of the pulsar as it's going at nearly the speed of light, and the material just whips away from it, and the magnetic field then excites that material to it's shocked and glowing in X-rays. But the jets are material that's going so fast as they slam in the interstellar medium, they make X-rays as well as glow by synchrotron radiation. So that's the interesting thing about the Vela Pulsar, which is a fantastic study, and it too is something that is visible, very difficult to see. In fact, it's only visible, the Vela Pulsar is only visible in X-rays. However, pulsars in general, the Crab is one, and there's another one called Geminga, and Geminga is primarily an X-ray, and gamma ray pulsar, but it's very close to the sky to the Crab. And the Geminga pulsar is a 24 millisecond, is a quarter of a second pulsar, which is another interesting one. They all pulse just like the others, and so we also can find that sometimes they come in binaries, because remember we talked a while back in a previous lecture that stars come in binaries? So sometimes we can get binary neutron stars, or neutron stars that are part of a binary system. And we can see X-rays that are happening in bursts. So then these happen in these, instead of pulses, bursts of X-rays that happen and then they fade. And maybe there's some pulsation that happens because there's neutron star activity, like a pulsar, and then all of a sudden there's a massive uptick in X-ray luminosity. And that's called an X-ray burster as part of a binary neutron star set, and that would kind of look like this. So if you have a neutron star, instead of a white dwarf now, remember the type 1 supernova was a white dwarf with a companion big star? Now imagine that it's a neutron star. Somehow a really massive star evolved, went supernova, its companion maybe received some of the material, or some of it was actually blown apart and accelerated the evolution of it. Now it becomes a red giant. As it becomes a red giant, it swells to fill the Roche lobe. Material falls once it gets close enough so that the gravitational field is greater than towards the neutron star than the center of the other star. It falls into a disk. There's a hot spot where it contacts that very, 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 very hot, dense disk. The disk is highly magnetized, of course, because it's a neutron star, and can bend the path of the material as it falls in. And since the magnetic field of a neutron star is much more powerful than a white dwarf, the path of it can then be redirected towards the poles, where all of a sudden it does these huge, huge, huge bursts of energy. And once it piles up enough stuff, there is massive thermonuclear explosions that can occur on the surface of the neutron star, And when they do that, we get a burst of X-rays. And so we get a binary neutron star making X-ray bursts. All right, so binary neutron stars are, well, their pulsars are roughly between 3/100ths of a second and about 1/3 of a second. And those are called millisecond, but a star like we showed can become a millisecond pulsar, or like 1/1000th of a second. And they had to get spun up. And so the act of falling onto the neutron star actually imparts the spin of the material orbiting it that then lands on it as it goes around and around and around. That spin of the disk and the material then imparts that onto the neutron star. And that's called and it can actually make the star go faster and faster. So when you have an X-ray burster, you should also have a millisecond pulsar. So let's see what that kind of looks like. So the donor star has material that's right on top. It creates a disk. Then you get these beam-like activities of X-rays happening in these beams. Now the rotation rate would be a lot faster than that because it's a pulsar, right? And so the magnetic field redirects the material onto the surface of the neutron star. The disk material falls on top of it, and as it does so, it gets more and more and more massive, and the angular momentum of the disk is imparted to the pulsar and spins and spins and spins faster and faster, spinning it up. So that's rather dizzying. I hope I'm not triggering anybody with any kind of problem. So this is what it might look like from above. You see the spinning material from the neutron star going around and around, and as it gets closer, it spins faster and faster until it gets redirected by the magnetic field to the poles onto the surface of it, and then spinning up the neutron star. So then what will happen is that after it spins up really fast, the material collects on the surface of the neutron star. And by collecting on the surface of the neutron star, it does an enormous X-ray burst as thermonuclear reactions occur. But remember that the escape speed from the surface of a neutron star can approach the speed of light, so these balls of fire, this fireball that you just saw at the end, can actually accumulate on the surface. And I'm actually just not going to show, I'll skip after this in just a second. But that fireball that we saw can actually accumulate on the surface and rotate with it, and when that burst comes along, that's what we see as the X-ray burst, because that light from all those that glows from the expanding hot gas, we see it as it glows and it comes into and out of our field of view, thus making an X-ray binary. All right, so binary neutron stars probably are more common because in globular clusters, which is interesting. Remember, globular clusters are always those old stars. So there must have been neutron stars formed in the youth of a globular cluster, and there must be binaries inside of them. So eventually those binaries can turn into total binaries. So maybe globular clusters have all these kind of things in them. And they're very dense stellar environments. So if they're spun up, you might have actually binary stars that might actually collide. So X-ray sources probably are millisecond pulsars, but you can't get the time resolution on something as distant as a globular cluster in order to know if they actually are millisecond pulsars. But to have so many bright X-ray sources in a globular cluster leads us to the suspicion that they are. All right, so maybe in that dense stellar environment of a globular cluster, two of the neutron stars can get close enough to collide. And that is what we can see here, is that eventually, if they get close enough to collide, they would spiral around each other in the center of this globular cluster, then the ancient stars as a pair of stars, and when they collide, they create a new kind of supernova called a kilonova. And a colliding neutron star makes a kilonova, which is an incredibly powerful supernova of two colliding neutron stars. All right, so we'll watch that video once again because that's kind of cool as they spin. And we actually have seen an observational evidence for such a kilonova occurring. And I'll show you what we mean again by this. There's a couple of colliding neutron stars. So this is the concept that was done inside of a supernova, inside of a collision simulation. And we can see that such a collision would take less than a second. It would take actually the final throes of it when the two neutron stars start to collide to when they merge into something, which is just a mess. It's its own new colliding object. Remember the density that it was? This is actually shredding those two things apart, which is astonishing that it could actually do that. So the combined magnetic field, speed rotation, orbital rotation, and density of these objects mean when they collide, they make a really, 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 really big explosion called a kilonova. And we'll talk about those things when we talk about gravitational waves in the future. So what happens when that happens? What happens if the remnant of the core is supermassive, meaning the core of a star is greater than, say, about 3 solar masses? If it's bigger than that, then the original star must have had a mass greater than 18 solar masses. If that's the case, and the star is more massive than about 18 solar masses, then neutron degeneracy, which is holding up these neutron stars and pulsars, that will fail. And if that fails, there's literally no pressure left in the cosmos that can hold the thing up against collapse, and the object collapses down to 0 radius at infinite density. Let's let that sit in for just a second. That's just an absurdity, but there we have it. We'll leave you with an absurdity that is a black hole. Black holes are bizarre, bizarre, bizarre objects. Remember how complex the neutron star was? Well, black holes are really simple. So it's kind of a weird thing to think that they are that simple.